Imagine being surrounded by relentless winds, each gust stronger than the last, tearing at everything in its path. Picture towering waves crashing down with an unstoppable force, their sheer power capable of swallowing entire cities. Visualize the sky turning dark as day becomes night, illuminated only by flashes of lightning that split the heavens with deafening thunder. Feel the ground tremble beneath your feet as massive storms unleash their fury, leaving a trail of destruction in their wake. Experience the intensity of nature's most extreme events, where survival is a constant battle against the elements. Witness the chaos as tornadoes twist and churn, their spiraling columns ripping through the landscape with unparalleled ferocity. See the overwhelming power of hurricanes, their monstrous eyes staring down with a calm yet menacing gaze, surrounded by walls of wind and rain that seem almost otherworldly. Understand the fear and awe inspired by these natural phenomena as they remind us of the immense and uncontrollable power of the planet we call home. As we embark on a journey through our solar system, we will encounter weather that makes Earth's fiercest storms seem tame in comparison. From the scorching heat of Venus to the colossal storms of Jupiter, each planet and moon offers a unique and terrifying glimpse into the extremes of atmospheric conditions. Prepare to be amazed by the unrelenting dust storms of Mars, which can engulf the entire planet, turning the sky a deep, foreboding red. Imagine standing on the surface of a gas giant, surrounded by turbulent clouds that stretch for thousands of kilometers, with winds that could tear apart any spacecraft. Explore the icy realms of Uranus and Neptune, where winds roar at supersonic speeds and storms rage with a cold, deadly intensity. Delve into the mysteries of Titan, Saturn's largest moon, where methane rains fall from the sky, creating alien landscapes that defy our earthly experiences. Join us as we uncover the secrets of Io, Jupiter's volcanic moon, where sulfur dioxide eruptions paint the surface in vibrant hues of yellow and red. Marvel at the beauty and danger of Enceladus, with its geysers of water ice shooting into space, hinting at hidden oceans beneath its frozen crust. Our voyage will take us to the far reaches of the solar system, where weather becomes a force of unimaginable scale and power. We will confront the unknown, facing environments that challenge our understanding and push the boundaries of human exploration. In these distant worlds, we find not just scientific curiosity, but a deeper appreciation for the delicate balance that sustains life on Earth. The stark contrast between our planet and these alien landscapes highlight the extraordinary conditions that make life possible here. As we navigate through the most dangerous weather in the solar system, we will gain new insights into the forces that shape our universe. The journey will be both humbling and inspiring, reminding us of the fragility and resilience of life in the face of such overwhelming power. Prepare yourself for a breathtaking adventure, where every moment brings new discoveries and challenges. The storms we will encounter are not just natural phenomena, but testaments to the dynamic and ever-changing nature of the cosmos. This exploration will take us beyond our comfort zones, pushing the limits of our imagination and scientific knowledge. Together, we will witness the raw power of the universe, learning more about our place within it and the forces that govern it. Join us as we embark on this epic journey, uncovering the most dangerous weather in the solar system and discovering what it means for the future of space exploration and our understanding of the universe. Across our solar system, the weather takes on forms more extreme and violent than anything found on Earth. On each planet and moon, unique atmospheric conditions create weather phenomena that defy imagination. Understanding these extraterrestrial weather systems helps us appreciate the diverse and dynamic nature of our cosmic neighborhood. In the scorching heat of Venus, temperatures soar high enough to melt lead. Its thick, toxic atmosphere traps heat in a runaway greenhouse effect, making it the hottest planet in our solar system. The perpetual cloud cover rains sulfuric acid, creating an environment more hellish than hospitable. Mars, with its thin atmosphere, experiences dust storms that can cover the entire planet for months. These colossal storms darken the sky and obscure the surface, making exploration a daunting task. The temperature swings are extreme, with daytime highs and nighttime lows creating a constant battle for survival. Jupiter's immense size generates weather on a scale unimaginable to us. The Great Red Spot, a storm larger than Earth, has been raging for centuries. Its winds and turbulence present a challenge for any mission daring to explore the gas giant's upper atmosphere. Saturn, famous for its rings, also boasts incredible weather systems. At its north pole, a mysterious hexagon-shaped storm rotates with a precision that puzzles scientists. The planet's vast storms and high-speed winds create a mesmerizing yet deadly environment. Uranus presents a unique case with its tilted axis, causing extreme seasonal variations. Its weather includes massive storms and high-speed winds that whip across its icy surface. The deep blue color of its atmosphere hides the violent activity beneath. Neptune, the furthest planet from the Sun, experiences the fastest winds in the solar system. Storms on Neptune can reach speeds of over 1,200 miles per hour, making it a planet of extremes. Its dark spots, akin to Jupiter's Great Red Spot, are areas of intense storm activity. Titan, Saturn's largest moon, has a thick atmosphere and liquid methane lakes. Its weather includes methane rainstorms and a climate that mimics early Earth. Titan's surface is a world where rivers and lakes of methane create an alien yet familiar landscape. Io, one of Jupiter's moons, is the most volcanically active body in our solar system. Its constant volcanic eruptions spew sulfur and other gases into space, creating a dynamic and hazardous environment. The surface is a tapestry of colors, shaped by continuous volcanic activity. Europa, another of Jupiter's moons, has a surface of ice with a subsurface ocean. Geysers of water vapor erupt through cracks in the ice, hinting at the potential for life beneath. The icy exterior and hidden ocean make Europa a focal point for astrobiological research. Enceladus, a moon of Saturn, also harbors an ocean beneath its icy crust. Geysers at its south pole eject water ice and organic molecules into space. These plumes offer clues about the moon's potential for harboring life and its geological activity. As we explore these distant worlds, we encounter weather systems that challenge our understanding and push the boundaries of science. Each planet and moon offers a glimpse into the diverse and powerful forces that shape our solar system. Our journey through the solar system's most dangerous weather takes us from the fiery surface of Venus to the icy expanses of Neptune. Each step reveals the complexity and beauty of weather phenomena beyond Earth. By studying these extreme environments, we gain insights into the processes that govern planetary atmospheres. Understanding extraterrestrial weather helps us prepare for future exploration and potential habitation. It also deepens our appreciation for Earth's relatively stable and life-supporting climate. As we continue to explore, we uncover the secrets of these distant worlds and the weather that defines them. Join us as we embark on an incredible journey through our solar system to uncover the most dangerous weather phenomena. We'll start by exploring Earth's most extreme weather events, giving us a baseline for understanding the chaos that awaits us on other planets. Next, we'll dive into the inferno that is Venus, with its scorching temperatures and sulfuric acid rain. From there, we'll travel to Mars, where massive dust storms can engulf the entire planet, creating a truly alien environment. Our journey will then take us to Jupiter, home of the Great Red Spot and other colossal storms that dwarf anything we experience on Earth. We'll visit Saturn to unravel the mysteries of its hexagon-shaped storm and its powerful, mesmerizing weather systems. After Saturn, we'll explore Uranus and Neptune, the ice giants, where supersonic winds and intense storms dominate their atmospheres. We'll also delve into the fascinating weather on some of the solar system's most intriguing moons, like Titan's methane rain and lakes. Io, with its continuous volcanic activity, offers a unique perspective on extraterrestrial weather driven by internal forces. Europa and Enceladus will show us icy surfaces and potential subsurface oceans, revealing geysers and other intriguing phenomena. Throughout our journey, we'll compare these extreme weather events to those on Earth, highlighting both similarities and stark differences. We'll discuss the implications of these weather systems for future space exploration and potential human habitation. Understanding these otherworldly weather patterns helps us appreciate the diversity of our solar system and the forces that shape it. We'll also examine the challenges and technological innovations needed to study and survive these harsh environments. By the end of our voyage, you'll have a new appreciation for the complexity and beauty of weather across the solar system. Prepare to be amazed, educated, and inspired as we explore the most dangerous weather in the solar system. The weather we encounter on other planets and moons poses significant challenges for future space exploration. Understanding these weather systems is crucial for designing robust spacecraft and habitats. Mars, with its frequent dust storms, could impact solar power generation and surface operations for human missions. Protective measures and advanced technologies will be essential to ensure the safety of astronauts. Venus, with its extreme heat and corrosive atmosphere, presents unique engineering challenges. Any missions to Venus will need to withstand intense temperatures and high atmospheric pressure. The violent storms on Jupiter and Saturn, along with their strong magnetic fields, require specially designed spacecraft to navigate safely. Future probes must be built to endure these harsh conditions for extended periods. Exploring the ice giants Uranus and Neptune means dealing with supersonic winds and extreme cold. Understanding their atmospheric dynamics will help us develop better instruments and probes for these distant planets. Titan's methane lakes and rivers offer a glimpse into an environment that could support life, albeit very different from Earth. Future missions to Titan will need to handle its dense atmosphere and liquid methane rain. Io's intense volcanic activity requires spacecraft that can withstand high radiation levels and the potential for sudden eruptions. Studying Io's weather and geological activity could provide insights into volcanic processes on Earth. Europa and Enceladus, with their subsurface oceans, hold the potential for discovering extraterrestrial life. Missions to these moons will need to penetrate their icy crusts and explore the hidden oceans below. Understanding the extreme weather on these celestial bodies helps us prepare for human missions beyond Earth. Developing technologies to cope with harsh conditions will be essential for the success and safety of these missions. Future space exploration will also benefit from studying weather patterns to predict and prepare for potential hazards. Advanced simulations and models will play a crucial role in mission planning and execution. Robotic missions and landers will need to be equipped with sensors and instruments capable of withstanding the extremes of temperature, pressure, and radiation found on other planets. Human habitats on Mars or other moons will require advanced life support systems and radiation shielding to protect astronauts from the harsh environments. Understanding local weather will help in selecting suitable sites for these habitats. Weather data from other planets can inform the design of future spacecraft, making them more resilient and capable of long-duration missions in the outer solar system. Studying extraterrestrial weather also enhances our knowledge of atmospheric science, which can be applied to improving weather prediction models on Earth. This interdisciplinary approach benefits both space exploration and our understanding of Earth's climate. As we push the boundaries of exploration, the knowledge gained from studying the solar system's most dangerous weather will drive innovation and inspire new generations of scientists and engineers. The challenges posed by extreme weather on other planets are daunting, but they also present opportunities for groundbreaking discoveries and technological advancements that will shape the future of space exploration. Earth's atmosphere is a delicate balance of gases that sustains life and shapes our weather systems. Composed mainly of nitrogen and oxygen, it also contains trace amounts of other gases, including carbon dioxide and water vapor. The atmosphere is divided into several layers, each with distinct characteristics. The troposphere, closest to the surface, is where all weather phenomena occur. It extends up to about 12 kilometers and contains most of the atmosphere's mass. Above the troposphere lies the stratosphere, home to the ozone layer, which protects us from harmful ultraviolet radiation. This layer extends from 12 kilometers to about 50 kilometers above the Earth's surface. The mesosphere, reaching up to 85 kilometers, is where temperatures drop dramatically and meteors often burn up. Above this layer is the thermosphere, which can reach temperatures of up to 2,500 degrees Celsius due to solar activity. The outermost layer, the exosphere, gradually fades into the vacuum of space. This layer extends from around 600 kilometers to 10,000 kilometers above the surface and contains very few particles. Weather on Earth is driven by the uneven heating of the planet's surface by the sun. This differential heating causes air to move, creating wind and distributing heat around the globe. The rotation of the Earth also influences weather patterns, contributing to the Coriolis effect. Water plays a crucial role in Earth's weather systems. The water cycle, involving evaporation, condensation, and precipitation, is essential for the formation of clouds, rain, snow, and other weather phenomena. Clouds form when warm, moist air rises and cools, causing water vapor to condense into tiny droplets or ice crystals. These clouds can lead to various types of precipitation, depending on atmospheric conditions. Storms are significant weather events that can have profound impacts. Thunderstorms, hurricanes, and tornadoes are driven by atmospheric instability and the presence of moisture. Each type of storm has unique characteristics and formation processes. Hurricanes, also known as cyclones or typhoons, are powerful tropical storms that form over warm ocean waters. They are characterized by strong winds, heavy rain, and a central eye of calm weather. Tornadoes are rapidly rotating columns of air that extend from thunderstorms to the ground. They can cause immense damage with their high wind speeds and erratic paths. Climate is the long-term pattern of weather in a particular area. Earth's climate is influenced by various factors, including solar radiation, volcanic activity, and human activities such as the burning of fossil fuels. The greenhouse effect is a natural process that warms the Earth's surface. Greenhouse gases, like carbon dioxide and methane, trap heat in the atmosphere, preventing it from escaping into space. This process is essential for maintaining temperatures that support life. However, human activities have increased the concentration of greenhouse gases, leading to global warming and climate change. These changes are affecting weather patterns, leading to more extreme weather events and altering ecosystems. Understanding Earth's atmosphere and weather systems is crucial for predicting weather, preparing for natural disasters, and addressing the impacts of climate change. The knowledge gained from studying our planet also provides a foundation for exploring the atmospheres of other planets in our solar system. Hurricanes and typhoons are among the most powerful and destructive weather phenomena on Earth. These massive tropical storms form over warm ocean waters and can grow to span hundreds of miles. The process begins with a cluster of thunderstorms over the ocean. When these storms draw energy from the warm water, they can start to organize and develop into a tropical depression. As the system strengthens, it becomes a tropical storm, and eventually, if conditions are right, it reaches hurricane or typhoon status. A hurricane or typhoon has a well-defined structure. At its center is the eye, a calm, clear area where the weather is relatively mild. Surrounding the eye is the eye wall, a ring of intense thunderstorms where the strongest winds and heaviest rains occur. The storm's spiral rain bands extend outward from the eye wall, bringing heavy rain and strong winds. These bands can stretch for hundreds of miles, affecting areas far from the storm's center. As the storm moves, it can cause widespread flooding and wind damage. The Saffir-Simpson Hurricane Wind Scale categorizes hurricanes into 5 categories based on their sustained wind speeds. Category 1 storms have winds of 74 to 95 miles per hour, while Category 5 storms have winds exceeding 157 miles per hour. The scale helps to estimate potential damage and necessary preparations. Warm ocean water is the primary fuel for hurricanes and typhoons. When sea surface temperatures reach at least 80 degrees Fahrenheit, they provide the energy needed for these storms to intensify. This is why hurricane and typhoon seasons typically occur in late summer and early fall. As a hurricane or typhoon moves over land or cooler water, it loses its energy source and begins to weaken. However, even a weakened storm can cause significant damage through heavy rainfall, flooding, and storm surge. Storm surge is one of the most dangerous aspects of hurricanes and typhoons. It occurs when strong winds push seawater onto the shore, leading to coastal flooding. The height of the surge depends on factors such as storm intensity, the shape of the coastline, and the tide level. Hurricanes and typhoons can have devastating impacts on communities. High winds can destroy buildings and infrastructure, while heavy rains can lead to landslides and flooding. The aftermath often includes long-term challenges such as power outages, water shortages, and health risks. Preparation and early warning systems are crucial for minimizing the impacts of these powerful storms. Advances in meteorology have improved our ability to predict the paths and intensities of hurricanes and typhoons, giving people more time to evacuate and secure their property. Climate change is expected to influence the frequency and intensity of hurricanes and typhoons. Warmer sea surface temperatures and changing atmospheric conditions could lead to more powerful storms and increased rainfall, exacerbating the risks associated with these events. Understanding the dynamics of hurricanes and typhoons is essential for building resilience in vulnerable regions. Research continues to improve our knowledge of these storms, leading to better forecasting models and more effective mitigation strategies. Efforts to protect coastal areas include building stronger infrastructure, restoring natural barriers like mangroves and wetlands, and implementing better land use planning. These measures can help reduce the damage caused by storm surge and flooding. International cooperation is also important in addressing the challenges posed by hurricanes and typhoons. Sharing data, technology, and best practices can enhance global preparedness and response efforts, saving lives and reducing economic losses. As we face a changing climate, our ability to understand and adapt to the threats of hurricanes and typhoons will be critical. By studying these powerful storms and investing in resilient infrastructure and communities, we can better protect ourselves and future generations. Tornadoes are among the most violent weather events on Earth, capable of causing immense destruction in a matter of minutes. These powerful columns of rotating air extend from thunderstorms to the ground, often leaving a path of devastation in their wake. The formation of a tornado begins within a severe thunderstorm, particularly those known as supercells. These storms have strong, rotating updrafts called mesocyclones, which are crucial for tornado development. When conditions are right, the rotation within the storm tightens and extends downward, creating a tornado. A tornado's intensity is measured using the enhanced Fujita scale, which ranges from EF0 to EF5. EF0 tornadoes have winds of 65-85 miles per hour and cause relatively minor damage, while EF5 tornadoes have winds exceeding 200 miles per hour, capable of obliterating entire buildings. Tornadoes can vary greatly in size and duration. Some are narrow, rope-like funnels that last only a few minutes, while others can be over a mile wide and stay on the ground for more than an hour, carving a long and wide path of destruction. The United States experiences more tornadoes than any other country, particularly in an area known as Tornado Alley. This region, which includes parts of Texas, Oklahoma, Kansas, and Nebraska, has the ideal conditions for tornado formation, including warm, moist air from the Gulf of Mexico and cold, dry air from the Rocky Mountains. Warning systems and preparedness plans are crucial for minimizing the impact of tornadoes. Meteorologists use radar to detect the rotation within thunderstorms and issue tornado watches and warnings to alert the public. When a warning is issued, it means a tornado has been sighted or indicated by radar, and immediate action should be taken. Tornadoes are highly unpredictable, and their paths can change rapidly. This makes them particularly dangerous, as there is often little time to react once a tornado is on the ground. Seeking shelter in a basement or an interior room on the lowest floor of a sturdy building is the best way to stay safe. The aftermath of a tornado can be devastating, with homes and infrastructure destroyed and lives lost or disrupted. Recovery can take months or even years, requiring significant resources and community support. Efforts to rebuild often focus on creating more resilient structures to better withstand future storms. Research into tornadoes continues to improve our understanding of these powerful storms. Scientists study the atmospheric conditions that lead to tornado formation, the dynamics of tornadoes themselves, and the best ways to predict and respond to them. This research is vital for enhancing our ability to forecast tornadoes and protect lives and property. Tornadoes also occur in other parts of the world, including Canada, Europe, Australia, and Asia. While less frequent than in the United States, these tornadoes can still cause significant damage and loss of life. Global efforts to study and understand tornadoes benefit all regions prone to these storms. The role of climate change in tornado activity is an area of ongoing research. Some studies suggest that changes in atmospheric conditions could affect the frequency, intensity, and distribution of tornadoes, though the exact impacts are still uncertain. Advancements in technology, such as improved radar systems and computer models, have enhanced our ability to detect and predict tornadoes. These tools allow for more accurate warnings and better informed decisions during severe weather events. Community education and preparedness are key components of tornado safety. Public awareness campaigns and drills help ensure that people know what to do when a tornado threatens. This knowledge can save lives and reduce injuries during these fast-moving storms. Building codes and construction practices in tornado-prone areas have also evolved to incorporate features that increase the resilience of structures. Reinforced walls, storm shelters, and other design elements help buildings withstand the powerful winds and flying debris associated with tornadoes. As we continue to learn more about tornadoes and improve our ability to predict and respond to them, we can better protect communities from these devastating storms. The knowledge gained from studying tornadoes contributes to our overall understanding of severe weather and enhances our preparedness for future events. Extreme temperatures, whether scorching heat waves or frigid polar vortexes, are significant weather phenomena that have profound impacts on our planet. These events challenge our ability to adapt and can have severe consequences for health, infrastructure, and the environment. Heat waves occur when high temperatures persist for an extended period. They are often accompanied by high humidity, which exacerbates the discomfort and health risks. These events can lead to heat exhaustion, heat stroke, and dehydration, posing a particular threat to vulnerable populations such as the elderly and children. Urban areas are especially prone to the effects of heat waves due to the urban heat island effect. Concrete and asphalt absorb and retain heat, causing cities to be significantly warmer than surrounding rural areas. This can lead to higher energy consumption as people rely on air conditioning to stay cool. Prolonged heat waves constrain power grids, leading to blackouts and disrupting essential services. They can also damage infrastructure, such as roads and railways, which may buckle under extreme heat. Additionally, the increased demand for water during heat waves can stress water supply systems. Agriculture is particularly vulnerable to heat waves, as crops can wilt and die under intense heat, leading to reduced yields and food shortages. Livestock can also suffer from heat stress, affecting their health and productivity. These impacts can have ripple effects on food prices and availability. On the opposite end of the spectrum, polar vortexes bring intensely cold air from the polar regions down to lower latitudes. These events can cause temperatures to plummet far below normal, creating dangerous and life-threatening conditions. A polar vortex occurs when the stratospheric winds that normally confine cold air around the poles weaken, allowing this frigid air to spill southward. The resulting cold snaps can affect large areas, bringing snow, ice, and freezing temperatures. Extreme cold poses numerous challenges. Frostbite and hypothermia are immediate health risks, especially for those without adequate shelter or clothing. The cold can also exacerbate existing health conditions, particularly respiratory and cardiovascular diseases. Infrastructure is significantly impacted by extreme cold. Water pipes can freeze and burst, leading to water shortages and costly repairs. Roads and bridges can become treacherous, hindering transportation and emergency response efforts. Energy demand spikes during cold snaps as people rely on heating to stay warm. This increased demand can strain power grids and lead to outages. The cold can also affect the functioning of power plants and other critical infrastructure, compounding the challenges. Both heat waves and polar vortexes are influenced by broader climatic patterns. Climate change is expected to increase the frequency and intensity of heat waves, making them more common and severe. There is also evidence that changes in the Arctic, such as the loss of sea ice, may influence the behavior of the polar vortex, potentially leading to more frequent or intense cold snaps. Preparing for extreme temperatures requires robust infrastructure and effective emergency response plans. Urban planning can help mitigate the impacts of heat waves through the use of green spaces and reflective materials to reduce heat absorption. Building codes can be updated to ensure structures are resilient to both extreme heat and cold. Public health initiatives are essential to protect vulnerable populations during extreme temperature events. Providing access to cooling centers during heat waves and warming shelters during cold snaps can save lives. Public awareness campaigns can educate people on how to stay safe and recognize the signs of heat-related and cold-related illnesses. Extreme temperatures also highlight the importance of reliable energy systems. Investments in grid resilience, energy efficiency, and renewable energy sources can help ensure that power remains available during extreme weather events. Diversifying energy sources can reduce the risk of outages and enhance overall system stability. As we continue to face the challenges posed by extreme temperatures, it is crucial to advance our understanding of these phenomena and their underlying causes. Research and innovation will play key roles in developing strategies to mitigate their impacts and enhance our resilience to a changing climate. As we delve deeper into the solar system, we'll encounter weather phenomena that make even Earth's most extreme events seem modest by comparison. Our journey will take us to worlds where the atmosphere and conditions are wildly different from anything we experience here. We'll start with Venus, a planet where surface temperatures soar high enough to melt lead and sulfuric acid rains down from thick, toxic clouds. Imagine a place so hostile, it defies our very concepts of weather. Next, we'll explore Mars, a cold desert world with dust storms that can engulf the entire planet, turning day into night and lasting for months. These storms reshape the Martian landscape and challenge our future missions. Jupiter's Great Red Spot is a storm so vast it could swallow Earth whole. This centuries-old tempest is just one of many colossal weather systems on the gas giant, where wind speeds reach unimaginable levels. Saturn, with its stunning rings, also hosts incredible storms. We'll look at the mysterious hexagon-shaped storm at its North Pole, a phenomenon unlike anything on Earth, and explore how such a pattern can form. The ice giants Uranus and Neptune present us with some of the most extreme weather in the solar system. With winds reaching supersonic speeds, these planets challenge our understanding of atmospheric dynamics. Titan, Saturn's largest moon, has weather that resembles a frozen, methane-filled version of Earth. Its thick atmosphere and liquid methane lakes offer a tantalizing glimpse into what weather might be like on a truly alien world. Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Its constant volcanic eruptions create a dynamic and hazardous environment, driven by tidal forces rather than atmospheric conditions. Europa and Enceladus, with their subsurface oceans, show us weather patterns influenced by both their icy exteriors and hidden liquid layers. Geysers of water ice erupting into space provide clues to their mysterious interiors. We'll also compare Earth's hurricanes and tornadoes to the massive storms on other planets, revealing the scale and intensity of extraterrestrial weather. These comparisons will highlight the unique and often extreme conditions found throughout our solar system. As we explore these distant worlds, we'll gain insights into the fundamental processes that drive weather, from the influence of solar radiation to the role of atmospheric composition. These discoveries will deepen our understanding of both Earth and the cosmos. Understanding the weather on other planets helps us prepare for future space missions and potential human habitation. By studying these extreme environments, we can develop technologies and strategies to survive and thrive beyond Earth. We'll see how different planetary atmospheres, from the thick clouds of Venus to the thin air of Mars, shape the weather and surface conditions. These comparisons will illuminate the diversity of climates within our own solar system. Join us as we embark on this extraordinary journey, uncovering the most dangerous and fascinating weather across the planets and moons. Each stop on our voyage will reveal new wonders and deepen our appreciation for the complexity of planetary weather. Prepare to be amazed by the incredible variety of weather phenomena that exist beyond our home planet. From scorching heat to frigid cold, from massive storms to constant volcanic activity, the solar system's weather is as diverse as it is extreme. Stay with us as we continue to explore the wonders of our solar system, comparing and contrasting Earth's weather with that of other planets. The adventure is just beginning, and the discoveries we make will change the way we see our own world and the universe around us. Venus, often called Earth's twin because of its similar size and composition, has an atmosphere that is anything but hospitable. The thick, toxic atmosphere of Venus is primarily composed of carbon dioxide, with clouds of sulfuric acid enveloping the planet. This dense atmosphere creates a runaway greenhouse effect, trapping heat and causing surface temperatures to soar to a scorching 900 degrees Fahrenheit. These temperatures are hot enough to melt lead, making Venus the hottest planet in our solar system. The atmospheric pressure on Venus is about 92 times greater than that of Earth, equivalent to being nearly a mile underwater. This immense pressure and heat make the surface conditions incredibly hostile to any form of life as we know it. Sulfuric acid clouds cover the planet, creating a highly reflective layer that makes Venus the brightest planet in our night sky. These clouds also lead to corrosive acid rain, which never reaches the surface but evaporates due to the extreme heat. Winds in the upper atmosphere of Venus can reach speeds of up to 220 miles per hour, much faster than the planet's slow rotation. This superrotation phenomenon means that the atmosphere circulates around the planet much faster than Venus itself rotates. Despite its harsh conditions, Venus has weather patterns that are surprisingly dynamic. The thick clouds and high-speed winds create storms and turbulence, adding to the planet's already extreme environment. The study of Venus's atmosphere provides valuable insights into the greenhouse effect and atmospheric dynamics. Understanding Venus helps scientists model climate systems and predict changes on Earth, especially related to global warming. Venus's surface is relatively young, geologically speaking, with vast plains, highland regions, and volcanic features. The intense heat and pressure have likely caused widespread volcanic activity, reshaping the planet's surface over time. Radar mapping missions like NASA's Magellan spacecraft have penetrated the thick clouds to reveal detailed images of Venus's surface. These missions have shown a world of rugged mountains, vast lava plains, and giant volcanoes. The exploration of Venus poses significant challenges due to its extreme conditions. Landers and probes must withstand immense pressure, heat, and corrosive chemicals, making Venus one of the most difficult planets to explore. Despite these challenges, missions to Venus continue to provide valuable data. Future missions aim to explore the planet's atmosphere and surface in greater detail, potentially revealing more about its history and evolution. Venus's atmosphere serves as a natural laboratory for studying the effects of extreme greenhouse conditions. The insights gained from Venus could help us understand the potential future of Earth's climate and the risks of runaway global warming. In addition to its scientific importance, Venus captivates our imagination with its bright presence in the sky and its dramatic, hellish conditions. It stands as a stark reminder of the diversity and extremes that exist within our solar system. Understanding Venus's atmosphere not only enriches our knowledge of planetary science but also underscores the importance of protecting our own planet's climate. The study of Venus is a poignant example of how planetary exploration can inform our stewardship of Earth. Join us as we delve deeper into the mysteries of Venus, uncovering the secrets of its thick, toxic atmosphere and extreme weather conditions. This journey will reveal the profound differences and surprising similarities between our two neighboring worlds. The runaway greenhouse effect on Venus is a dramatic example of how a planet's climate can spiral out of control. It occurs when a planet's atmosphere traps so much heat that it causes temperatures to rise uncontrollably. On Venus, this process began with water vapor in the atmosphere. Early in its history, Venus may have had oceans, much like Earth. However, being closer to the Sun, it received more solar radiation, causing more water to evaporate. Water vapor is a powerful greenhouse gas. As more water entered the atmosphere, it trapped additional heat, causing the surface temperature to rise further. This increased evaporation, creating a feedback loop. Eventually, the heat was so intense that any remaining water boiled away entirely. The water vapor rose into the upper atmosphere, where it was broken down by solar radiation into hydrogen and oxygen. The lighter hydrogen atoms escaped into space. With the water gone, carbon dioxide became the dominant greenhouse gas. Volcanic activity on Venus released massive amounts of carbon dioxide into the atmosphere. Without water to absorb it, carbon dioxide accumulated, intensifying the greenhouse effect. The thick carbon dioxide atmosphere trapped heat very efficiently, leading to the extreme surface temperatures we see today. This process locked Venus into a state of perpetual high temperatures and high atmospheric pressure. Unlike Earth, where carbon dioxide is cycled between the atmosphere, oceans, and living organisms, Venus has no such mechanisms to remove CO2 from the atmosphere. This means the greenhouse effect on Venus continues unabated. The runaway greenhouse effect on Venus serves as a warning about the potential consequences of unchecked greenhouse gas emissions. It shows how a planet's climate can reach a tipping point beyond which it cannot recover. On Earth, the greenhouse effect is essential for maintaining temperatures that support life. However, human activities, particularly the burning of fossil fuels, are increasing levels of carbon dioxide and other greenhouse gases in our atmosphere. Understanding the runaway greenhouse effect on Venus helps scientists predict how similar processes might unfold on Earth if greenhouse gas emissions continue to rise. It underscores the importance of addressing climate change to avoid catastrophic consequences. Studying Venus provides a stark contrast to Earth's relatively balanced climate system. It highlights the delicate interplay between atmospheric composition, solar radiation, and planetary temperature. The insights gained from Venus emphasize the need for sustainable environmental practices. By learning from our neighboring planet, we can better appreciate the importance of preserving Earth's climate stability. Future missions to Venus aim to gather more data on its atmospheric composition and dynamics. This information will further our understanding of the runaway greenhouse effect and its implications for other planets, including exoplanets in distant solar systems. Venus's extreme conditions also challenge our technological capabilities. Developing instruments and probes that can survive its harsh environment pushes the boundaries of engineering and innovation. The surface temperature on Venus is a scorching 900 degrees Fahrenheit, hot enough to melt lead. This makes Venus the hottest planet in our solar system, even hotter than Mercury, which is closer to the Sun. This intense heat is due to the thick atmosphere composed primarily of carbon dioxide. The dense clouds of sulfuric acid reflect sunlight, but the heat that does reach the surface is trapped, unable to escape back into space. The atmospheric pressure on Venus is about 92 times greater than Earth's at sea level. It's equivalent to the pressure found nearly a mile underwater on Earth. This immense pressure would crush most human-made structures and make survival impossible without advanced technology. The combination of high temperatures and crushing pressure creates an environment that is incredibly hostile. Any spacecraft landing on Venus must be specially designed to withstand these extreme conditions. Despite these challenges, missions like the Soviet Union's Venera program have successfully landed probes on Venus, providing valuable data about its surface and atmosphere. These missions revealed a rocky, barren landscape, with temperatures and pressures unlike anything on Earth. The thick atmosphere not only traps heat, but also creates a greenhouse effect that prevents the planet from cooling down. This runaway greenhouse effect has caused Venus to remain in a state of perpetual extreme heat. In the upper atmosphere, winds reach speeds of up to 220 miles per hour. These superrotational winds circulate the planet much faster than Venus rotates, creating dynamic weather patterns despite the static conditions on the surface. The surface itself is relatively young, geologically speaking, with vast plains, highland regions, and large volcanic structures. The intense heat and pressure have likely caused extensive volcanic activity, continuously reshaping the planet's landscape. Radar mapping missions, such as NASA's Magellan, have penetrated the thick clouds to reveal detailed images of Venus's surface. These maps show features like Maxwell Montes, the highest mountain on Venus, and vast lava flows indicative of past volcanic activity. The oppressive conditions on Venus make it an intriguing subject of study, offering insights into the extremes of planetary science. Understanding how Venus's atmosphere and surface interact under such conditions helps scientists refine their models of planetary atmospheres and climates. Exploring Venus challenges our technological capabilities, pushing the limits of what our spacecraft and instruments can endure. Future missions aim to further explore its atmosphere and surface, shedding light on the planet's history and evolution. The study of Venus's extreme temperatures and atmospheric pressure also has implications for exoplanet research. Planets with thick atmospheres and high temperatures might be more common than previously thought, influencing our search for habitable worlds. High-speed winds on Venus are a fascinating and extreme feature of its atmosphere. These winds can reach up to 220 miles per hour in the upper cloud layers, significantly faster than the planet's rotation. The phenomenon of superrotation causes the atmosphere to spin around Venus much quicker than the planet itself. While Venus takes 243 Earth days to complete one rotation, its upper atmosphere completes a full rotation in just about 4 Earth days. This superrotation creates dynamic weather patterns high above the surface, despite the more static conditions below. The winds carry clouds of sulfuric acid across the planet at incredible speeds, shaping the climate and atmospheric circulation. The driving forces behind these high-speed winds are complex and not yet fully understood. Factors like solar heating, the planet's slow rotation, and atmospheric tides all contribute to this unique atmospheric behavior. These powerful winds are primarily confined to the upper atmosphere, where they whip around the planet in a continuous, planet-wide jet stream. At lower altitudes, the winds decrease dramatically, moving at just a few miles per hour near the surface. The differences in wind speeds between the upper and lower atmosphere create significant vertical wind shear, This shear can influence cloud formation and the distribution of atmospheric particles, further complicating the planet's weather patterns. Studying these high-speed winds helps scientists understand the dynamics of planetary atmospheres, particularly those with thick, dense compositions like Venus. It also offers insights into the atmospheric behavior of exoplanets with similar characteristics. The exploration of Venus's winds involves both observational missions and sophisticated computer models. Spacecraft like the European Space Agency's Venus Express have provided crucial data, revealing details about wind speeds, directions, and atmospheric pressure. These high-speed winds also play a role in Venus's extreme weather phenomena, such as its thick cloud cover and heat distribution. The winds help circulate heat around the planet, contributing to the uniform high temperatures observed on the surface. Despite the hostile conditions, future missions aim to study Venus's atmosphere in greater detail. Balloons or aerial platforms could float in the upper atmosphere, directly sampling the winds and providing real-time data on their behavior and effects. Understanding the winds on Venus also helps scientists draw comparisons with other planets. For instance, the study of atmospheric dynamics on gas giants like Jupiter and Saturn, which also have fast-moving jet streams, benefits from the knowledge gained on Venus. These high-speed winds highlight the complexity and diversity of planetary weather systems. They challenge our existing theories and push the boundaries of our understanding, driving innovation in both observation techniques and atmospheric modeling. Visual simulations of Venus's wind patterns offer a glimpse into the planet's complex and dynamic atmosphere. These simulations reveal how the winds circulate and interact at different altitudes. At high altitudes, the simulations show the fast-moving jet streams that encircle the planet. These jet streams drive the superrotation, with winds racing around Venus much quicker than its surface rotates. The sulfuric acid clouds, carried by these jet streams, form a swirling pattern that can be seen in ultraviolet light. This creates a mesmerizing display of shifting, rotating clouds that continuously morph and change shape. Further down, the simulations depict a marked decrease in wind speeds. Near the planet's surface, the winds are much calmer, moving only a few miles per hour. This stark contrast highlights the vertical wind shear within Venus's atmosphere. These visualizations also capture the thick, turbulent cloud cover that shrouds the planet. The clouds, driven by high-altitude winds, create a dense and impenetrable layer that reflects sunlight and traps heat. Using data from missions like Venus Express, scientists can simulate how heat is distributed by these winds. The visual simulations show how the winds help circulate thermal energy around the planet, contributing to Venus's uniform surface temperatures. The simulations often use color coding to represent different wind speeds and directions. This provides a clear and intuitive way to understand the complex flow patterns within Venus's atmosphere. They also highlight the role of atmospheric waves and tides, which can influence wind patterns. These waves propagate through the atmosphere, interacting with the jet streams and adding further complexity to the wind dynamics. In some simulations, we see the effects of solar heating on the atmosphere. As the sun heats one side of the planet, it drives the movement of air masses, creating day-night temperature contrasts that affect wind speeds and directions. The visualizations can also illustrate the impact of Venus's slow rotation. Unlike Earth, which has a rapid day-night cycle, Venus's rotation period is so long that it significantly affects atmospheric circulation and weather patterns. The role of the planet's topography can be seen in some simulations, showing how surface features like mountains and plains influence the movement of air masses. This interaction between the surface and atmosphere adds another layer of complexity to the wind patterns. These simulations are not just scientific tools, they also provide a visually striking way to appreciate the alien nature of Venus's atmosphere. The swirling, dynamic visuals help convey the extreme conditions and powerful forces at work on the planet. By comparing these simulations with those of Earth's atmosphere, we can better understand the similarities and differences in planetary weather systems. This comparison offers valuable insights into how different atmospheric conditions can shape weather patterns. Future missions and more advanced simulations will continue to refine our understanding of Venus's winds. As technology improves, we can expect even more detailed and accurate visualizations that reveal the intricate dance of winds on this scorching planet. The clouds of Venus are composed mainly of sulfuric acid, creating a thick, toxic layer that encircles the entire planet. These clouds form at high altitudes, where sulfur dioxide and water vapor undergo chemical reactions driven by sunlight. The sulfuric acid clouds are highly reflective, bouncing sunlight back into space and making Venus one of the brightest objects in our night sky. Despite this reflectivity, the planet's surface remains incredibly hot due to the greenhouse effect below. Sulfur dioxide in Venus's atmosphere comes from volcanic activity. This gas rises into the upper atmosphere, where it reacts with water vapor to produce sulfuric acid. The resulting droplets form dense clouds that cover the planet. These clouds are not only dense but also highly corrosive. They consist of concentrated sulfuric acid, which is capable of eroding and breaking down materials that would be considered resilient on Earth. The formation of sulfuric acid rain begins with the condensation of these acid droplets in the high-altitude clouds. However, unlike rain on Earth, this sulfuric acid rain evaporates before reaching the surface due to the extreme heat in the lower atmosphere. The constant cycle of evaporation and condensation creates a perpetual cloud cover that never dissipates. This thick blanket of clouds maintains the planet's harsh surface conditions and prevents direct observation of the surface from space. Sulfuric acid rain poses significant challenges for any spacecraft attempting to study Venus. The corrosive nature of the acid requires specially designed instruments and protective coatings to withstand the hostile environment. Understanding the chemistry behind these sulfuric acid clouds is crucial for scientists. It offers insights into the atmospheric processes of Venus and helps in modeling the planet's climate and weather patterns. The presence of sulfuric acid also influences the thermal structure of the atmosphere. By absorbing and reflecting sunlight, these clouds play a key role in the energy balance of Venus, contributing to its extreme temperatures. The clouds are layered with variations in density and composition at different altitudes. This stratification affects the movement of heat and the circulation of winds, adding to the complexity of Venus's atmospheric dynamics. Instruments on spacecraft like Venus Express have measured the composition and behavior of these clouds, providing valuable data that helps scientists understand the planet's extreme environment. The high reflectivity of the clouds means that only a small fraction of sunlight reaches the surface. Despite this, the trapped heat from the greenhouse effect keeps the surface temperatures consistently high. The sulfuric acid in the clouds also contributes to the planet's distinctive yellowish appearance when observed from space. This coloration is a result of the scattering of sunlight by the acid droplets. The clouds extend up to about 70 kilometers above the surface, forming a thick, impenetrable barrier. This makes direct observation of the surface challenging, requiring the use of radar to map the planet's topography. Studying these sulfuric acid clouds not only reveals the harsh realities of Venus, but also enhances our understanding of atmospheric chemistry and cloud formation processes that can apply to other planetary bodies and exoplanets. The surface of Venus is profoundly affected by its extreme atmospheric conditions. The intense heat and crushing pressure create a landscape unlike any other in our solar system. The volcanic plains and mountains are constantly subjected to temperatures that can melt lead. This means that any hypothetical exploration vehicles must withstand extraordinary heat and pressure. The surface rocks on Venus are thought to be primarily basalt, formed from volcanic activity. However, their composition might be altered by the harsh chemical environment, particularly the presence of sulfur compounds from the atmosphere. The high temperatures and pressures also mean that liquid water cannot exist on the surface. Any water that might have been present in Venus's past would have evaporated long ago, contributing to the greenhouse effect. If we imagine standing on Venus, the sky would appear a yellowish color due to the thick sulfuric acid clouds above. The intense pressure would make it feel like being deep underwater on Earth. Explorations of the surface reveal vast lava plains, indicating extensive volcanic activity. Some of these lava flows appear relatively young, suggesting that Venus might still be volcanically active today. Hypothetical scenarios for future missions include deploying advanced landers capable of withstanding the extreme conditions. These landers would need to be heavily shielded against the heat and corrosive atmosphere. Understanding the surface conditions helps scientists simulate what might happen if a spacecraft or even a human mission were to land on Venus. These simulations are critical for designing equipment that can survive long enough to send back valuable data. Imagining a human presence on Venus is challenging. Any habitats would need to be highly insulated and pressurized, with robust cooling systems to manage the extreme heat. Life support systems would be under constant strain in such an environment. The intense surface conditions also raise questions about the planet's geological history. Researchers study surface features to understand how Venus evolved over billions of years under such extreme pressures and temperatures. Exploring hypothetical scenarios also includes the idea of aerial platforms or balloons that could float in the upper atmosphere where conditions are less hostile. These platforms could provide long-term monitoring of Venus's atmospheric processes. The impact of the sulfuric acid clouds on surface materials is significant. Any lander or instrument must be made from materials resistant to corrosion, ensuring they can operate effectively despite the harsh environment. Scientists also consider the possibility of discovering life in the more temperate upper layers of Venus's atmosphere. This would require missions designed to search for microbial life that could exist in acidic cloud droplets. Hypothetical scenarios extend to what Venus might look like if its atmosphere were altered. Terraforming Venus is a concept that explores the idea of transforming its environment to make it more Earth-like, though this remains purely speculative. Studying Venus's surface and imagining these scenarios helps us appreciate the planet's unique challenges and the technological innovations needed for exploration. The insights gained from Venus can inform our understanding of other extreme environments in the solar system and beyond. Mars, often called the Red Planet, has a thin atmosphere composed primarily of carbon dioxide. This atmosphere is just 1% as dense as Earth's, making it incapable of supporting liquid water on the surface. The sky on Mars often appears pink or orange due to the fine dust particles suspended in the atmosphere. These particles scatter sunlight, creating the planet's characteristic hues. Mars experiences significant temperature variations. Daytime temperatures near the equator can reach up to 70 degrees Fahrenheit, but at night they can plummet to minus 100 degrees Fahrenheit due to the thin atmosphere's inability to retain heat. The surface of Mars is a cold desert, featuring vast plains, towering volcanoes, and deep canyons. The largest volcano, Olympus Mons, is about 3 times the height of Mount Everest, showcasing the planet's dramatic geology. Valles Marineris, a canyon system on Mars, stretches over 2,500 miles long and reaches depths of up to 4 miles. It dwarfs Earth's Grand Canyon and offers insights into the tectonic processes that have shaped Mars. Mars's surface is covered with iron oxide or rust, which gives the planet its reddish appearance. This dust is fine and pervasive, often getting into equipment and posing challenges for exploration missions. Polar ice caps on Mars are composed of water and carbon dioxide ice. These ice caps expand and contract with the seasons, revealing layers that provide clues to the planet's climatic history. The thin atmosphere means that Mars has no protective magnetic field, exposing the surface to higher levels of cosmic radiation. This lack of protection poses a significant challenge for future human missions. Dust storms are a common feature on Mars. Some of these storms can grow to cover the entire planet, lasting for weeks or even months and significantly affecting surface conditions and visibility. Mars has a variety of surface features, including impact craters, which provide a record of the planet's history. These craters, some hundreds of miles across, tell stories of ancient collisions with asteroids and comets. The presence of dried-up riverbeds and minerals that form in the presence of water suggests that Mars once had a wetter, more hospitable environment. These findings fuel the search for past life on the planet. Robotic missions like the rovers Curiosity and Perseverance have been exploring Mars's surface, conducting experiments and sending back detailed images. These missions aim to uncover the planet's geological history and assess its potential for future human habitation. Mars's thin atmosphere allows for more dramatic changes in surface temperature and weather patterns compared to Earth. The lack of significant atmospheric pressure also means that water would boil away quickly if exposed on the surface. Mars has 2 small moons, Phobos and Deimos, which are thought to be captured asteroids. These moons add to the dynamic environment of Mars, each presenting unique features and mysteries of their own. As we explore Mars, we continue to learn about its complex environment, the history recorded in its rocks and soil, and the potential it holds for future exploration and possibly even colonization. The study of Mars not only enhances our understanding of the red planet, but also offers valuable lessons about planetary science and the conditions that might support life elsewhere in the solar system. Martian dust storms are a defining feature of the red planet's climate, occurring with remarkable frequency and sometimes growing to encompass the entire planet. These storms are driven by the planet's thin atmosphere and its temperature fluctuations. When sunlight heats the Martian surface, it causes the thin air to rise, creating winds that can lift dust particles off the ground. Once airborne, these fine particles can remain suspended for days, weeks, or even months. During a dust storm, the sky can turn a reddish-brown color, blocking out sunlight and drastically reducing visibility. This thick haze can obscure surface features and make navigation challenging for robotic missions. Dust storms on Mars range in size from small localized events to massive planet-wide storms. Localized storms can cover areas as small as a few square kilometers, while global storms can envelop the entire planet. The largest dust storms occur during Mars's southern summer, when the planet is closest to the Sun. The increased solar heating during this time leads to more vigorous atmospheric activity and the potential for more extensive dust lifting. These global dust storms can last for several months, and they have a significant impact on the planet's climate. The dust absorbs sunlight, warming the atmosphere and preventing heat from escaping back into space. The duration and intensity of these storms can pose serious challenges for missions to Mars. Solar panels on rovers and landers can become coated with dust, reducing their ability to generate power and potentially leading to mission failures. NASA's Opportunity rover, for example, ultimately succumbed to a massive dust storm in 2018, which coated its solar panels and prevented it from recharging its batteries. This highlighted the harsh conditions that can suddenly arise on Mars. Dust storms also contribute to the erosion of surface features. The abrasive particles, carried by high winds, can slowly wear down rocks and other geological formations, altering the landscape over time. Understanding the dynamics of Martian dust storms is crucial for planning future missions. Scientists study the frequency, duration, and driving forces behind these storms to better predict their occurrence and impact. Monitoring Martian weather from orbit helps to provide advance warning of incoming storms. Spacecraft like the Mars Reconnaissance Orbiter continuously observe the planet's atmosphere, tracking the development and movement of dust storms. The dust itself is composed of fine, iron-rich particles that give Mars its characteristic red color. These particles are so small that they can remain suspended in the air for extended periods, contributing to the longevity of dust storms. The impact of dust storms on potential human missions to Mars is a major consideration. Shielding habitats and equipment from the abrasive effects of the dust will be essential, as will finding ways to ensure a reliable power supply despite the reduced sunlight. Exploring the mechanisms behind these storms not only informs us about Mars, but also provides insights into atmospheric processes on other planets with thin atmospheres. It highlights the complex interactions between surface conditions and atmospheric dynamics. As we continue to study Martian dust storms, we gain a deeper understanding of the challenges and opportunities that lie ahead in the exploration of the red planet. These insights will be critical for designing resilient missions and ultimately paving the way for human exploration. One of the most notable Martian dust storms occurred in 1971 during NASA's Mariner 9 mission. As the spacecraft approached Mars, it encountered a planet-wide dust storm that obscured the entire surface. Mariner 9 became the first spacecraft to orbit another planet, but it had to wait for weeks before the dust settled enough to start mapping the Martian surface. In 2001, Mars experienced another significant global dust storm that lasted for several months. This storm was closely monitored by multiple spacecraft, including the Mars Global Surveyor and the Hubble Space Telescope, providing valuable data on how these storms evolve and affect the planet. The Mars exploration rovers, Spirit and Opportunity, faced numerous dust storms during their missions. In 2007, a series of large storms threatened both rovers, reducing their power levels as dust covered their solar panels. Despite the challenges, both rovers managed to survive by conserving energy and waiting for the storms to pass. In 2018, a massive dust storm enveloped Mars, becoming one of the most extensive on record. This storm led to the loss of communication with the Opportunity rover, which had been exploring Mars since 2004. The thick dust clouded the atmosphere for months, blocking sunlight and preventing Opportunity from recharging its batteries, ultimately ending its mission. The Curiosity rover, which relies on a nuclear power source instead of solar panels, continued its operations during the 2018 storm. This event highlighted the advantages of using alternative power sources to ensure mission resilience in the face of unpredictable weather. Dust storms have also affected the InSight lander, which studies Mars's interior. Dust accumulation on its solar panels has reduced its power supply, prompting the mission team to carefully manage energy usage to continue its scientific operations. Orbital missions like the Mars Reconnaissance Orbiter and the Mars Atmosphere, and Volatile Evolution, or MAVEN, have provided critical observations of dust storms from above. These spacecraft track storm development, movement, and the impact on the atmosphere, offering insights that are essential for future missions. The data collected from these missions help scientists understand the seasonal patterns of dust storms on Mars. This knowledge is crucial for planning safe landing sites and operational strategies for future rovers and human missions. Mars's thin atmosphere allows dust to be lifted easily, but also means that it takes a long time for the dust to settle once airborne. This creates long-lasting effects on the surface and poses challenges for maintaining clean solar panels and other equipment. The experiences from past missions emphasize the importance of designing robust systems that can withstand the harsh conditions on Mars. Future missions will likely incorporate lessons learned, such as improved dust mitigation techniques and the use of power sources less dependent on sunlight. Dust storms not only impact power and visibility, but can also affect communication with Earth. The charged dust particles can interfere with radio signals, making it difficult to send and receive data during a storm. Understanding the interaction between Martian dust storms and the planet's overall climate is a key area of research. These storms can redistribute dust and gases across the planet, influencing long-term weather patterns and surface conditions. As we prepare for human exploration of Mars, the impact of dust storms on habitats, equipment, and human health will be a major consideration. Ensuring that astronauts can safely navigate and maintain operations during these storms is essential for mission success. The historical dust storm events on Mars have provided invaluable lessons and highlighted the resilience and adaptability needed for successful exploration. Each mission builds on the knowledge gained from previous encounters, paving the way for more advanced and sustainable exploration of the red planet. Temperature variations between day and night on Mars are dramatic, showcasing the planet's inability to retain heat. During the day, especially near the equator, temperatures can reach a relatively warm 70 degrees Fahrenheit. However, as soon as the sun sets, the lack of a thick atmosphere causes the temperatures to plummet rapidly. Nighttime temperatures can drop to -100 degrees Fahrenheit, a stark contrast to the daytime warmth. These extreme fluctuations are primarily due to Mars's thin atmosphere, which is about 100 times less dense than Earth's. Without a substantial atmospheric blanket, the heat from the sun quickly dissipates into space. This lack of atmospheric insulation means that heat absorbed by the surface during the day is lost almost immediately after sunset. As a result, Martian nights are incredibly cold, regardless of the daytime temperature. Such temperature swings pose significant challenges for both robotic and potential human missions. Equipment and habitats must be designed to withstand rapid cooling and prevent freezing during the night. Rovers like Curiosity are equipped with heaters to keep their instruments at operational temperatures. These heaters draw energy from the rover's power supply, which needs to be carefully managed to ensure continuous operation. The thin atmosphere also means that the surface of Mars cools down very quickly once the sun goes down. This rapid cooling can cause thermal stresses on materials, potentially leading to cracks and mechanical failures over time. For human explorers, temperature regulation will be crucial. Habitats will need advanced insulation and heating systems to maintain a stable internal environment despite the external temperature swings. Mars's polar regions experience even more extreme temperature variations due to their location. During the winter, temperatures can drop below -195 degrees Fahrenheit, while summer days can be relatively warmer. Understanding these temperature variations helps scientists plan for the thermal protection of equipment and the health and safety of future astronauts. Detailed knowledge of temperature cycles aids in selecting materials that can endure such harsh conditions. Temperature changes also affect the Martian soil and regolith. The expansion and contraction due to heating and cooling can influence the stability of the surface, impacting the design of landing pads and other infrastructure. The large temperature differences between day and night are also responsible for some of the weather patterns observed on Mars. As the surface heats and cools, it creates air currents that contribute to the planet's dynamic atmospheric behavior. Dust on Mars plays a role in moderating these temperature swings. During dust storms, the airborne particles can reduce the amount of sunlight reaching the surface, leading to cooler days and slightly warmer nights. Research into these temperature variations provides insights into the planet's energy balance and climatic processes. It helps refine models that predict weather patterns and surface conditions, essential for mission planning. As we prepare for extended human presence on Mars, managing the effects of these extreme temperature variations will be a critical aspect of ensuring the safety and success of the missions. Future missions to Mars face a myriad of potential dangers that must be meticulously planned for. One of the primary concerns is radiation exposure. Without a protective magnetic field like Earth's, Mars is bombarded by cosmic rays and solar radiation. Extended exposure to this radiation can pose serious health risks to astronauts, including increased cancer risk and damage to bodily tissues. Effective shielding and protective measures will be essential for ensuring astronauts' safety. Another significant danger is the Martian dust. The fine, pervasive dust can infiltrate equipment, potentially causing malfunctions or damage. For human missions, inhaling this dust could be harmful, requiring robust filtration systems in habitats and spacesuits. The extreme temperature variations between day and night present a challenge for both technology and human survival. Habitats and suits will need advanced thermal regulation systems to cope with the rapid and severe temperature changes. Mars's thin atmosphere means that landing spacecraft safely is more complex. The lack of significant atmospheric drag requires precise control of entry, descent, and landing systems to ensure a safe touchdown. Dust storms can disrupt solar power generation, which many missions rely on. These storms can last for weeks or even months, necessitating alternative energy sources or sufficient battery storage to maintain operations during extended periods of low sunlight. Communication delays between Earth and Mars, which can range from 4 to 24 minutes one way, complicate real-time decision-making. Autonomous systems and artificial intelligence will be critical for handling immediate issues that arise. The reduced gravity on Mars, about 38% of Earth's, poses long-term health challenges for astronauts. Prolonged exposure to low gravity can lead to muscle atrophy and bone density loss, requiring rigorous exercise regimens and medical monitoring. Water extraction and purification will be vital for sustaining human missions. Mars has ice, but developing efficient methods to access and process this water is a major technical hurdle that must be overcome. The psychological effects of isolation and confinement on Mars missions are another danger. The long duration of the missions, combined with the vast distance from Earth, can lead to mental health challenges for crew members. The potential for mechanical failures or unexpected problems with life support systems poses a constant risk. Redundant systems, regular maintenance, and the ability to repair or improvise solutions on the spot will be crucial. Mars's surface conditions, including the rough and varied terrain, can be hazardous for exploration rovers and astronauts. Navigation and mobility solutions must account for the planet's rocky landscape and potential obstacles. Human missions will also need to address the logistics of food production and storage. Ensuring a reliable and sustainable food supply will be essential for long-term missions, possibly through innovative methods like hydroponics or other forms of controlled environment agriculture. The possibility of encountering unknown biological hazards, such as Martian microbes, albeit low, cannot be entirely ruled out. Comprehensive sterilization procedures and protocols for handling potential biohazards will be necessary. Successful future missions will require extensive preparation, advanced technology, and a deep understanding of the Martian environment. Overcoming these dangers is essential for the safe and effective exploration and eventual habitation of Mars. Mitigating the dangers of Mars missions requires a comprehensive approach, combining advanced technology, rigorous planning, and innovative solutions. For radiation protection, habitats and spacecraft can be designed with enhanced shielding materials, such as polyethylene or water, to absorb harmful particles. Developing underground habitats or using Martian regolith to build protective structures can further reduce radiation exposure. These measures utilize the natural shielding provided by the planet's surface. To address the pervasive Martian dust, advanced air filtration systems and sealed habitats will be crucial. Regular maintenance and cleaning protocols can prevent dust from damaging equipment or endangering crew health. Thermal regulation systems in habitats and spacesuits will need to be highly efficient to cope with Mars's extreme temperature variations. Phase change materials and active heating and cooling systems can help maintain stable internal temperatures. For safe landings, precision landing technologies like autonomous guidance systems and advanced parachutes or retropropulsion will ensure accurate and gentle touchdowns on the Martian surface. Energy resilience can be achieved by incorporating nuclear power sources, such as radioisotope thermoelectric generators, alongside solar panels. These can provide continuous power during dust storms and long Martian nights. Autonomous systems equipped with artificial intelligence can handle routine tasks and immediate issues, reducing reliance on delayed Earth communication. These systems can monitor habitat conditions, perform repairs, and manage life support systems. Countermeasures for low gravity include specialized exercise equipment to maintain muscle and bone health. Astronauts can use resistance machines and centrifuges to simulate gravity and reduce physical degradation. Water extraction technologies will focus on drilling and heating subsurface ice. Systems to purify and recycle water will ensure a sustainable supply, vital for drinking, agriculture, and hygiene. Psychological support strategies will include virtual reality environments to provide mental stimulation and social interaction. Regular communication with Earth and structured routines can help maintain mental health. Redundant life support systems are essential to handle mechanical failures. Modular systems that can be easily repaired or replaced ensure continuous operation and reduce the risk of catastrophic failures. Advanced navigation tools, including drones and autonomous rovers, can map and scout terrain ahead of human explorers. These tools help avoid hazards and plan efficient routes for surface missions. Food security on Mars can be achieved through hydroponics and aquaponics, which allow for efficient soil-less agriculture. Utilizing nutrient-rich water and controlled environments can produce a reliable food supply. Sterilization procedures for all incoming and outgoing materials will prevent biological contamination. Stringent protocols and quarantine measures will protect both Mars and Earth from potential biohazards. International collaboration and shared resources can enhance mission safety and success. Pooling knowledge, technology, and expertise from multiple space agencies will create robust mitigation strategies for Mars exploration. Jupiter's atmosphere is an immense, swirling mix of hydrogen and helium, with trace amounts of methane, ammonia, and water vapor. This gaseous envelope extends thousands of miles deep, creating a complex and dynamic weather system. The planet's atmosphere is characterized by its colorful bands, which are composed of alternating zones of high and low pressure. These bands create the striking, striped appearance of Jupiter that we can see through telescopes. Jupiter's upper atmosphere is divided into several layers. The troposphere, where most weather phenomena occur, contains clouds made primarily of ammonia ice. Below this layer lies the stratosphere, which has fewer clouds and is warmer due to the absorption of solar radiation. The most prominent feature in Jupiter's atmosphere is the Great Red Spot, a massive storm that has been raging for at least 400 years. This anticyclonic storm is larger than Earth and showcases the violent weather dynamics of the gas giant. Beneath the visible clouds, Jupiter's atmosphere transitions gradually into the planet's deeper layers. As pressure increases, the hydrogen gas becomes denser and eventually turns into a liquid. This liquid metallic hydrogen is a unique state of matter not found on Earth. Jupiter's structure is dominated by this vast ocean of liquid metallic hydrogen, which generates the planet's powerful magnetic field. This magnetic field is the strongest in the solar system, extending millions of miles into space and trapping charged particles. The core of Jupiter is still a subject of research and debate. It is believed to be composed of a dense mixture of elements, possibly surrounded by a layer of metallic hydrogen. The exact composition and state of the core remain elusive due to the extreme conditions. Jupiter's rapid rotation, completing a spin every 10 hours, contributes to its dynamic atmosphere. This fast rotation causes the planet to bulge at the equator and flattens at the poles, creating strong centrifugal forces. The immense gravity of Jupiter influences its moons and the surrounding space environment. Its gravitational pull is so strong that it affects the orbits of other objects in the solar system, acting as a kind of cosmic vacuum cleaner by capturing comets and asteroids. The cloud bands and storms on Jupiter are driven by complex interactions between internal heat and solar radiation. Despite being far from the Sun, Jupiter radiates more heat than it receives due to the slow gravitational compression of the planet's massive atmosphere. Jupiter's upper atmosphere contains auroras near the poles, created by the interaction of the magnetic field with solar wind particles. These auroras are much more powerful than those on Earth and are a spectacular display of the planet's magnetic activity. The intense radiation belts around Jupiter pose a challenge for spacecraft. These belts, filled with high-energy particles, can damage electronics and pose risks to any mission attempting to study the planet up close. The outer atmosphere of Jupiter is also home to lightning storms, which are far more powerful than those on Earth. These lightning bolts are thought to occur within water clouds deep in the atmosphere, providing a glimpse into the planet's meteorological processes. The interaction between Jupiter's atmosphere and its moons, especially Io, adds another layer of complexity. Io's volcanic activity is influenced by Jupiter's gravitational forces, and material from Io contributes to the planet's magnetosphere. Studying Jupiter's atmosphere and structure helps scientists understand the formation and evolution of gas giants. These insights not only reveal the nature of our own solar system, but also aid in the study of exoplanets orbiting distant stars. The Great Red Spot is one of Jupiter's most iconic features, a massive storm larger than the Earth itself. It has been raging for at least 400 years, possibly much longer, making it one of the longest-lasting storms known in the solar system. This gigantic storm is an anticyclonic system, meaning it rotates counterclockwise in the southern hemisphere of Jupiter. The winds in the Great Red Spot reach speeds of up to 400 miles per hour, significantly faster than any storm on Earth. The spot's reddish color remains a mystery, though it is thought to be caused by chemicals like phosphorus, sulfur, or organic compounds reacting with ultraviolet light from the sun. These interactions create the vivid hues observed in the storm. At its widest, the Great Red Spot spans about 10,000 miles, large enough to fit Earth within it. However, observations have shown that it has been gradually shrinking over the past century. Despite this, it remains a dominant feature on Jupiter. The storm is situated between two jet streams flowing in opposite directions, which helps to contain and maintain its shape. These jet streams create a turbulent environment, yet the Great Red Spot has managed to sustain itself amidst these chaotic forces. The storm extends deep into Jupiter's atmosphere, possibly reaching depths of several hundred miles. This vertical structure contributes to its intensity and longevity, with the deeper layers feeding energy into the system. NASA's Juno spacecraft has provided unprecedented views of the Great Red Spot, revealing intricate details about its structure and dynamics. Juno's instruments have measured the storm's gravity, magnetic field, and thermal emissions, offering insights into its inner workings. The Great Red Spot's interaction with surrounding cloud bands generates waves and turbulence, affecting weather patterns across a wide area. These interactions help scientists understand the dynamics of large-scale storms on gas giants. Despite its stability over centuries, the storm exhibits changes over shorter timescales. The size, shape, and color of the Great Red Spot can vary, influenced by complex atmospheric processes that are still not fully understood. One theory for the storm's persistence is the lack of a solid surface on Jupiter. Unlike Earth's hurricanes, which dissipate when they make landfall, the Great Red Spot has no solid barrier to weaken it, allowing it to endure for centuries. Energy for the Great Red Spot is thought to come from Jupiter's internal heat and the complex interactions of its atmosphere. The planet radiates more energy than it receives from the Sun, driving powerful atmospheric dynamics. The storm's longevity and size make it an excellent natural laboratory for studying fluid dynamics and atmospheric physics. Researchers use the Great Red Spot to test models that can apply to both Jupiter and other planetary atmospheres. Changes in the Great Red Spot offer clues about broader changes in Jupiter's atmosphere. Monitoring these variations helps scientists track the planet's climate and understand the forces shaping its weather patterns. The Great Red Spot has inspired a wealth of scientific inquiry and continues to captivate astronomers and planetary scientists. Its sheer scale and enduring presence make it a focal point for understanding the complexities of gas giant atmospheres. As we continue to study the Great Red Spot, we gain valuable insights into the nature of storms, atmospheric dynamics, and the fundamental processes driving weather on other planets. This knowledge enriches our understanding of the solar system and beyond. Historical observations of the Great Red Spot date back to the 17th century. The first recorded observation is often attributed to the Italian astronomer Giovanni Cassini in 1665. He described a permanent storm visible through early telescopes. Throughout the 18th and 19th centuries, astronomers continued to observe the Great Red Spot, noting its persistent presence and distinctive coloration. These observations helped establish the storm as a long-term feature of Jupiter. The storm's visibility has varied over time, with some periods where it was less prominent. However, it has remained a focal point for planetary astronomers studying Jupiter's atmospheric dynamics. In the 20th century, advances in telescope technology provided more detailed views of the Great Red Spot. Observations from ground-based telescopes and later space missions revealed its complex structure and immense scale. The Voyager missions in the late 1970s provided the first close-up images of the Great Red Spot. Voyager 1 and 2 captured stunning details of the storm, including its swirling clouds and turbulent edges, transforming our understanding of this colossal feature. The Hubble Space Telescope has continuously monitored the Great Red Spot since the 1990s. Hubble's high-resolution images have documented changes in the storm's size, shape, and color, offering a long-term perspective on its evolution. Current understanding of the Great Red Spot has been greatly enhanced by the Juno mission, which arrived at Jupiter in 2016. Juno's close passes over the storm have provided unprecedented data on its depth, temperature, and internal structure. Juno's microwave radiometer has revealed that the Great Red Spot extends deep into Jupiter's atmosphere, much deeper than previously thought. This finding suggests that the storm is fueled by internal processes within the planet. The spacecraft's gravity measurements have also shown variations in the storm's mass distribution, indicating complex dynamics at play within the Great Red Spot. These insights help scientists model the storm's behavior more accurately. Despite its persistent presence, the Great Red Spot has been shrinking over the past century. Historical data combined with modern observations show that the storm is gradually becoming smaller, though it remains a dominant feature on Jupiter. The reasons for the storm's shrinkage are not fully understood, but it may involve changes in Jupiter's atmospheric dynamics or a gradual loss of energy over time. Continued monitoring will be crucial to unraveling this mystery. Research indicates that the Great Red Spot's reddish color may be due to chemicals brought up from deeper in the atmosphere by the storm's powerful updrafts. Laboratory experiments on Earth aim to replicate these conditions to better understand the storm's hue. The storm's longevity is partly attributed to Jupiter's lack of a solid surface. Unlike terrestrial storms that dissipate upon encountering land, the Great Red Spot can continue unabated due to the gas giant's uniform atmospheric composition. The storm's energy source is thought to be a combination of Jupiter's internal heat and the planet's rapid rotation. These factors drive the intense winds and complex weather patterns seen within the Great Red Spot. Ongoing observations and future missions will continue to enhance our understanding of the Great Red Spot. By studying this immense storm, scientists gain valuable insights into atmospheric processes that can apply to other planets, both within and beyond our solar system. Jupiter is home to a variety of massive storms beyond the Great Red Spot. One notable example is the Oval BA, often referred to as Red Spot Junior, which formed from the merging of smaller white ovals in 2000. Oval BA is smaller than the Great Red Spot, but still an impressive storm. It has been observed to change color from white to red, indicating complex atmospheric processes at work. Another significant storm system on Jupiter is the North Temperate Belt disturbance. This system is characterized by a series of large white ovals that periodically appear and merge. creating long-lasting storms. The South Equatorial Belt, one of Jupiter's most prominent cloud bands, frequently experiences large-scale upheavals. Periodically, this belt undergoes dramatic changes, including fading and reappearing, influenced by powerful atmospheric currents. The planet's polar regions are particularly turbulent. Juno's observations have revealed clusters of cyclones at both poles, with storms arranged in intricate patterns that are unique to each pole. At Jupiter's North Pole, the cyclones form a central cyclone surrounded by 8 smaller ones, creating a striking geometric arrangement. The South Pole features a similar pattern, but with 5 surrounding cyclones. These polar cyclones are massive, each spanning thousands of miles. They represent some of the most intense and enduring weather systems in the solar system. Lightning storms on Jupiter are another fascinating aspect of its weather. These storms are much more powerful than those on Earth, with lightning bolts that are several times more energetic. Lightning on Jupiter is thought to occur in deep water clouds, where conditions are similar to those that produce thunderstorms on Earth. The presence of these storms suggests dynamic weather patterns and significant moisture deep within the atmosphere. Jupiter's equatorial region features fast-moving jet streams that create alternating bands of cloud tops moving in opposite directions. These bands result in complex weather interactions and frequent storm formation. The gas giant's rapid rotation, completing a rotation in just under 10 hours, contributes to these intense jet streams. The Coriolis effect caused by this rapid spin helps maintain the structure of the various atmospheric bands and storm systems. Interactions between these jet streams and storm systems can lead to the formation of new vortices and weather patterns. This dynamic environment makes Jupiter's atmosphere one of the most complex and active in the solar system. Periodic eruptions from Jupiter's moon Io also impact the planet's weather. Volcanic plumes from Io can inject large amounts of sulfur dioxide into Jupiter's atmosphere, influencing cloud formation and coloration. The interaction between Io's volcanic activity and Jupiter's magnetosphere creates auroras at the planet's poles, adding another layer of complexity to its atmospheric dynamics. Studying these various storm systems and weather patterns on Jupiter helps scientists understand the underlying physics of gas giant atmospheres. Each observation adds to our knowledge of how these massive planets function and evolve over time. Visual simulations of Jupiter's weather patterns provide stunning insights into the planet's dynamic atmosphere. These simulations are generated using data from spacecraft, telescopes, and advanced computer models. One of the most striking features in these simulations is the banded structure of Jupiter's atmosphere. The alternating light and dark bands, known as zones and belts, are vividly rendered, showing the intense jet streams that drive their motion. The simulations highlight the Great Red Spot, illustrating its rotation and interaction with surrounding cloud bands. Watching the storm's swirling motion helps to understand its immense energy and persistence. Simulations of the polar regions reveal the complex arrangements of cyclones. The geometric patterns of these storms are shown in detail, offering a clear view of their stability and structure. These visualizations also depict lightning storms deep within Jupiter's atmosphere. Bright flashes represent powerful lightning bolts, providing clues about the intense convective activity driving these storms. By modeling the planet's rapid rotation, simulations show the influence of the Coriolis effect. This helps explain the formation of the distinct bands and the chaotic turbulence within the atmosphere. The merging and formation of smaller storms into larger ones, like Oval BA, are captured in simulations. This process shows the dynamic nature of Jupiter's weather, where small disturbances can evolve into significant features. Interactions between different atmospheric layers are illustrated, revealing how deep atmospheric processes influence surface weather patterns. The movement of gases and heat from the interior to the upper layers is crucial for understanding Jupiter's climate. Simulations also show the impact of external factors, such as the volcanic activity on Io. Plumes of sulfur dioxide from Io are seen spreading through Jupiter's atmosphere, affecting cloud formation and auroras. The energy balance within Jupiter's atmosphere is another focus of these simulations. They depict how heat from the planet's interior and solar radiation drive the atmospheric dynamics, creating a constantly changing environment. Time-lapse simulations provide a compressed view of how storms and bands evolve over months or years. This perspective helps to appreciate the long-term changes and trends in Jupiter's weather. The role of ammonia clouds in Jupiter's weather is highlighted, showing how these clouds form, dissipate, and interact with other atmospheric elements. Understanding these clouds is key to unraveling the complexities of Jupiter's meteorology. Auroras at Jupiter's poles are vividly portrayed, demonstrating their connection to the planet's magnetic field and interaction with the solar wind. These visualizations help to understand the energetic processes behind these spectacular light shows. Simulations also explore hypothetical scenarios, such as the effect of varying internal heat or changes in the planet's rotation. These scenarios provide insights into how different factors might alter Jupiter's atmospheric behavior. By combining observational data with theoretical models, these visual simulations offer a comprehensive and detailed understanding of Jupiter's weather. They are invaluable tools for scientists and captivating visuals for anyone interested in the wonders of our solar system. Wind speeds on Jupiter are some of the fastest in the solar system, with jet streams that can reach up to 400 miles per hour. These high-speed winds create the planet's distinctive banded appearance and drive its complex weather patterns. The winds in the Great Red Spot are particularly intense, circulating at speeds of up to 400 miles per hour. This enormous storm has been sustained by these powerful winds for centuries, maintaining its position in Jupiter's atmosphere. Jupiter's rapid rotation, completing a full spin every 10 hours, significantly influences these wind speeds. The Coriolis effect generated by this rapid rotation helps to maintain the strong jet streams that encircle the planet. The equatorial region of Jupiter features some of the fastest winds, moving in opposite directions to the winds in the higher latitudes. This creates a dynamic and turbulent boundary between the different atmospheric bands. These extreme wind speeds contribute to the formation and longevity of massive storms, including the Great Red Spot and Oval BA. The interaction of these winds with Jupiter's internal heat sources drives the continuous activity in the atmosphere. Lightning phenomena on Jupiter are also remarkably powerful, far exceeding the energy of lightning on Earth. These lightning storms occur deep within the planet's atmosphere, often within water clouds. Jupiter's lightning strikes are thought to be up to 1,000 times more powerful than those on Earth. The intense flashes illuminate the cloud tops, providing a spectacular light show visible from space. The lightning is generated by the same basic principles as on Earth. Collisions between ice particles within the clouds create static electricity. The resulting lightning bolts discharge enormous amounts of energy. Juno's instruments have detected and recorded these lightning flashes, revealing their frequency and distribution across the planet. The data shows that lightning is more common near Jupiter's poles than at its equator. The presence of lightning indicates active weather systems and deep convective activity within Jupiter's atmosphere. These storms transport heat from the deep atmosphere to the upper layers, contributing to the planet's overall energy balance. The interaction between the lightning and Jupiter's magnetic field generates radio waves, known as whistlers. These signals can be detected by spacecraft and provide additional information about the planet's atmospheric conditions. Lightning storms on Jupiter also contribute to the creation of complex chemical compounds in the atmosphere. The high-energy strikes can break apart molecules, leading to the formation of new chemical species. The study of lightning and wind phenomena on Jupiter helps scientists understand the dynamics of gas giant atmospheres. These insights are crucial for understanding not only Jupiter, but also other gas giants and exoplanets with similar characteristics. Wind speeds and lightning are key elements of Jupiter's weather, driving the formation of storms and influencing the planet's atmospheric chemistry. By studying these phenomena, scientists gain a deeper appreciation of the forces shaping Jupiter's environment. As we continue to explore Jupiter with missions like Juno, the data on wind speeds and lightning will enhance our understanding of the planet's meteorological processes and contribute to our broader knowledge of planetary science. When comparing Jupiter's storms to those on Earth, the differences in scale and intensity are immediately apparent. Earth's most powerful hurricanes and tornadoes, while destructive, are dwarfed by the sheer size and strength of Jupiter's atmospheric phenomena. The Great Red Spot, for instance, is larger than the entire Earth and has persisted for centuries. No storm on Earth comes close to its size or longevity. Our most intense storms typically last only a few weeks at most. Wind speeds in Jupiter's storms can reach up to 400 miles per hour, far exceeding the highest recorded wind speeds in Earth's hurricanes. which max out around 200 miles per hour. This incredible wind velocity drives the violent and turbulent weather on Jupiter. Earth's storms are driven primarily by solar heating, with warm ocean waters providing the energy for hurricanes. On Jupiter, internal heat plays a significant role, with the planet radiating more energy than it receives from the sun, fueling its massive storms. Lightning on Jupiter is much more powerful than on Earth, with strikes up to 1,000 times stronger. While lightning on Earth occurs in thunderstorms across various climates, Jupiter's lightning is concentrated in its polar regions and deep atmospheric layers. Jupiter's rapid rotation contributes to the formation of its fast-moving jet streams and banded cloud patterns. Earth's rotation also influences weather patterns, creating the Coriolis effect that shapes cyclones and trade winds, but the effect is far more pronounced on Jupiter. The storms on Jupiter can merge and interact in ways that are rare on Earth. For example, the formation of oval BA from the merging of smaller storms demonstrates a complexity in storm dynamics not typically seen in Earth's atmosphere. The polar cyclones on Jupiter, arranged in geometric patterns at both poles, have no direct Earth counterpart. While Earth's polar regions do experience cyclonic activity, it is far less organized and intense compared to Jupiter's persistent polar cyclones. Dust storms on Earth, like those in deserts or regions of intense drought, are minor compared to the planet-wide dust storms that can envelop Mars. However, Jupiter's atmosphere does not support dust storms. Instead, its weather is dominated by gas and liquid dynamics. Auroras on both planets are spectacular, but Jupiter's are far more powerful. Jupiter's magnetic field interacts with its moons and solar wind to create auroras hundreds of times more energetic than those on Earth. Earth's hurricanes are typically measured on the Saffir-Simpson scale, ranging from Category 1 to Category 5. Jupiter's storms, lacking a solid surface and with vastly different atmospheric conditions, require different metrics for their classification and study. The duration of Jupiter's storms is also significantly longer. While Earth's hurricanes dissipate as they lose access to warm ocean waters, Jupiter's storms can last for years, maintained by the planet's internal heat and atmospheric dynamics. Comparing the energy sources, Earth's storms rely on solar energy and the planet's water cycle. Jupiter's storms harness both solar and significant internal heat, driving more intense and persistent weather systems. The overall structure of storms on both planets shows that despite the differences, some fundamental atmospheric processes are universal. Convection, pressure systems, and rotation influence weather patterns, albeit on vastly different scales. Understanding these differences and similarities enhances our comprehension of atmospheric science. Studying Jupiter's colossal storms provides insights that improve our models of Earth's weather, offering a broader perspective on the forces shaping planetary climates. Saturn's atmosphere is composed primarily of hydrogen and helium, similar to Jupiter, but it also contains trace amounts of methane, ammonia, and other gases. This gaseous composition gives Saturn its characteristic pale yellow hue. The planet's atmosphere features bands of clouds, though they are less distinct than those on Jupiter. These bands are driven by high-speed winds that can reach up to 1 to 100 miles per hour, making them some of the fastest in the solar system. Saturn's upper atmosphere is divided into several layers. The visible clouds are primarily made of ammonia ice, while deeper layers contain water ice and ammonium hydrosulfide. These layers create complex weather patterns and storm systems. Map. One of the most famous features of Saturn's atmosphere is the hexagon-shaped storm at its north pole. This mysterious, six-sided jet stream is unlike anything seen elsewhere in the solar system, rotating with near-perfect symmetry. The hexagon is surrounded by powerful winds and storms, creating a dynamic and turbulent region. Scientists believe the hexagon is caused by differences in wind speed at different latitudes, but its precise mechanics are still under study. Saturn's atmosphere is also home to massive storms that can rival those on Jupiter. These storms can be several times larger than Earth and often last for months, creating dramatic changes in the planet's cloud patterns. In addition to its fascinating atmosphere, Saturn is renowned for its extensive ring system. These rings are composed mostly of ice particles, along with rock and dust, creating a stunning and complex structure encircling the planet. The rings are divided into several main sections, labeled alphabetically in the order they were discovered. The most prominent of these are the A, B, and C rings, which are easily visible through telescopes. Each ring is made up of countless individual particles, ranging in size from tiny grains of dust to large chunks several meters across. These particles orbit Saturn at varying speeds, creating intricate patterns and gaps within the rings. The Cassini division is a well-known gap between the A and B rings, caused by the gravitational influence of Saturn's moon Mimas. This division is one of many gaps and structures within the rings created by the gravitational interactions with Saturn's moons. Saturn's rings are incredibly thin relative to their width, measuring only about 30 feet thick on average, yet they span over 175,000 miles from edge to edge. This thinness makes them delicate and complex structures. The origin of Saturn's rings is still a topic of research. They may be remnants of a destroyed moon or leftover material from the planet's formation. Understanding their origin can provide insights into the history of the solar system. The rings also cast shadows on Saturn's atmosphere, creating beautiful and ever-changing patterns. These shadows help scientists study the vertical structure of the rings and the planet's atmospheric dynamics. Saturn's ring system is not static. It evolves over time due to gravitational interactions, collisions, and other processes. Studying these changes helps scientists understand the dynamics of ring systems and their interactions with host planets. Saturn's atmosphere and rings together create one of the most visually striking and scientifically intriguing systems in the solar system. Their study continues to reveal new insights into planetary science and the processes that shape our cosmic neighborhood. The hexagon storm at Saturn's North Pole is one of the most intriguing and unique features in our solar system. First discovered by the Voyager spacecraft in the 1980s, it has fascinated scientists for decades. This massive storm is shaped like a hexagon, a perfect six-sided figure that spans about 20,000 miles across. Each side of the hexagon is roughly the diameter of Earth, highlighting its immense scale. Unlike any weather pattern seen on other planets, the hexagon rotates with near-perfect stability. It completes a full rotation approximately every 10 hours, matching Saturn's rotation period. The hexagon's structure is thought to be caused by a jet stream moving at different speeds. This differential rotation creates a standing wave pattern, resulting in the hexagonal shape. At the center of the hexagon lies a circular storm, similar to a hurricane on Earth but much larger. This central storm features an eye and high-speed winds, adding to the complexity of the polar weather system. The edges of the hexagon are defined by powerful winds, blowing at speeds of about 200 miles per hour. These winds maintain the hexagon's shape and prevent it from dissipating, despite the turbulent environment. The hexagon's color changes with the seasons on Saturn, appearing blue during winter and more golden as the planet moves towards summer. These color changes are likely due to variations in sunlight and atmospheric composition. Infrared images from the Cassini spacecraft have provided detailed views of the hexagon. These images reveal the storm's vertical structure, showing that it extends deep into Saturn's atmosphere. The hexagon also appears to be a stable, long-lasting feature. It has persisted for at least 4 decades and possibly much longer, indicating a level of atmospheric stability that is still not fully understood. Scientists use fluid dynamics models to study the hexagon, attempting to recreate its formation in laboratory settings. These experiments help to understand the underlying physics driving such a unique atmospheric phenomenon. The hexagon's stability and persistence challenge our understanding of planetary weather systems. On Earth, similar wave patterns are unstable and transient, making the hexagon's long-term stability particularly puzzling. The storm provides a natural laboratory for studying atmospheric dynamics on a grand scale. By understanding the forces that maintain the hexagon, scientists can gain insights into the behavior of fluid systems in general. Observations of the hexagon also offer clues about Saturn's atmospheric composition and thermal structure. The behavior of the storm reflects broader processes at work in the planet's atmosphere. As Saturn's seasons change, continued observations of the hexagon will reveal how it responds to varying solar radiation and other environmental factors. These observations are crucial for building comprehensive models of Saturn's atmosphere. The hexagon storm at Saturn's North Pole remains one of the most captivating and mysterious features in the solar system. Its study continues to inspire and challenge scientists, offering glimpses into the complex and dynamic nature of planetary atmospheres. Possible explanations for the hexagon storm at Saturn's North Pole involve complex atmospheric dynamics. One leading theory suggests that the hexagon, is a standing wave pattern in the planet's atmosphere, created by a jet stream moving at different speeds. To visualize this, imagine a continuous flow of gas moving around the pole. Variations in the wind speeds create waves that eventually stabilize into a hexagonal shape. These waves are similar to those seen in rotating fluids on Earth, but on a much larger scale. Another theory proposes that the hexagon is the result of interactions between Saturn's atmospheric jet streams and the planet's rotation. The rapid rotation of Saturn, combined with differential wind speeds, could generate the stable, six-sided shape. Computer simulations have been crucial in understanding the hexagon. Models of Saturn's atmosphere show that certain conditions, like specific wind speeds and rotation rates, can indeed produce a hexagonal wave pattern. Laboratory experiments also help visualize the hexagon. By rotating a cylindrical tank of fluid at different speeds, scientists can create similar polygonal shapes, supporting the idea that differential rotation and wind speeds are key factors. The hexagon's vertical structure provides additional clues. Infrared images from Cassini show that the storm extends deep into Saturn's atmosphere. This vertical extension might contribute to its stability and long lifespan. Visualization of temperature variations within the hexagon reveals that the storm is warmer in the center and cooler along the edges. These temperature gradients play a role in maintaining the shape and dynamics of the storm. The color changes of the hexagon with the seasons offer insights into Saturn's atmospheric composition. Visualizations of these changes help scientists understand how sunlight and atmospheric chemistry interact over time. Another intriguing aspect is the presence of smaller vortices within the hexagon. These smaller storms interact with the hexagon's jet stream, creating complex patterns that are visualized in high-resolution images. The hexagon's interaction with Saturn's magnetic field could also play a role. Visualizations of magnetic field lines show how they might influence the atmospheric dynamics at the poles, contributing to the hexagon's stability. Observations of similar, though less stable, polygonal shapes on other planets and moons provide comparative visualizations. For example, polygonal patterns in polar regions of gas giants like Neptune suggest that such formations could be more common than previously thought. Simulating the hexagon under different hypothetical conditions, such as varying wind speeds or atmospheric composition, helps scientists test various theories. These visualizations are key to refining our understanding of this unique phenomenon. The hexagon's symmetry and persistence make it an excellent subject for visualizations in both scientific research and public outreach. Animations showing its rotation and internal dynamics captivate audiences and highlight the complexities of planetary atmospheres. By combining observations, simulations, and laboratory experiments, scientists create detailed visualizations that offer a comprehensive picture of the hexagon. These efforts continue to unravel the mysteries of Saturn's atmospheric dynamics. The ongoing study of the hexagon storm, through both theoretical models and visualizations, provides invaluable insights into the behavior of fluid systems in rotating atmospheres. This research not only enhances our understanding of Saturn, but also contributes to the broader field of planetary science. Saturn hosts other significant storms beyond the famous hexagon at its North Pole. One notable example is the Great White Spot, a massive storm that appears approximately once every Saturnian year, which is about 30 Earth years. The Great White Spot can span tens of thousands of miles, encircling the planet and disrupting the atmosphere with its intense activity. It marks the onset of Saturn's summer solstice in the northern hemisphere and drastically alters weather patterns. These storms begin as small, bright clouds that rapidly grow in size and intensity. As they expand, they generate powerful winds and create turbulence across Saturn's atmosphere, leading to dramatic changes in the planet's appearance. Another significant storm system on Saturn is the series of long-lived large-scale vortices found in its mid-latitudes. These storms, often referred to as Saturn's giant storms, can persist for several years and influence the surrounding atmosphere. In 2010, the Cassini spacecraft observed one of the most powerful storms ever recorded on Saturn. This storm, located in the northern hemisphere, was so large it encircled the entire planet, creating a massive band of disturbed clouds and intense lightning. Saturn's southern hemisphere also features significant storm activity. The region is known for generating massive, long-lasting storms that contribute to the dynamic and ever-changing nature of Saturn's atmosphere. Smaller storms, known as convective storms, frequently erupt in Saturn's equatorial regions. These storms are driven by upwelling currents of warmer gas, which rise and cool, forming bright, turbulent cloud tops visible from space. Saturn's polar regions are home to unique storms distinct from the hexagon. The South Pole, in particular, features a large, hurricane-like vortex with a clearly defined eye, surrounded by towering clouds that rotate rapidly around it. These polar storms are incredibly powerful, with wind speeds reaching up to 300 miles per hour. They offer valuable insights into the atmospheric dynamics at Saturn's poles and the processes driving such intense weather systems. Storms on Saturn often produce intense lightning, similar to but more powerful than those on Earth. Cassini's observations revealed that lightning strikes within these storms can be up to 10,000 times more energetic than those on our home planet. The frequency and intensity of Saturn's storms provide a wealth of data for scientists studying planetary atmospheres. Each storm event contributes to our understanding of how these massive systems form, evolve, and interact with the broader atmospheric conditions. Observing these storms helps scientists understand the energy balance within Saturn's atmosphere. The heat from the planet's interior, combined with solar radiation, drives the turbulent weather patterns and storm formation. Storms on Saturn also interact with the planet's ring system. The gravitational pull from the rings can influence atmospheric conditions, leading to the formation of new storms or altering existing ones. By studying the variety and behavior of Saturn's storms, scientists gain a deeper appreciation of the complexities of gas giant atmospheres. This research not only enhances our knowledge of Saturn, but also provides comparative data for understanding other planets in our solar system and beyond. Continued observation and analysis of Saturn's storms through missions like Cassini and future endeavors will further unravel the mysteries of this dynamic planet, offering new insights into the powerful forces shaping its atmosphere. Visual simulations of Saturn's storms provide an in-depth look at the dynamics driving these massive weather systems. These simulations combine data from spacecraft like Cassini with advanced computer models to recreate the storms in stunning detail. One of the most striking features in these simulations is the Great White Spot. Visualizations show how this storm rapidly grows from a small cloud into a colossal weather system, encircling the entire planet. Simulations highlight the storm's violent nature, with swirling clouds and turbulent winds that stretch for tens of thousands of miles. The interaction of the storm with Saturn's atmospheric bands creates dramatic and complex patterns. The simulations also capture the frequent lightning strikes within these storms. Bright flashes illuminate the clouds, emphasizing the immense energy released during these powerful events. Polar storms, including the hexagon and the hurricane-like vortex at the South Pole, are rendered in detailed simulations. These visualizations show the unique geometric shape of the hexagon and the spiraling clouds of the polar hurricane. By visualizing temperature gradients, the simulations reveal the thermal dynamics within the storms. Warmer gases rise and cool as they move outward, driving the convective processes that sustain these massive systems. The interactions between Saturn's storms and its ring system are another focus of these simulations. Visualizations show how the gravitational pull from the rings influences atmospheric conditions, leading to the formation of new storms. Convective storms in the equatorial regions are depicted as well. These simulations highlight the upwelling of warmer gas and the resulting bright cloud tops, providing insights into the storm formation process. Visualizations of the 2010 superstorm capture its scale and intensity. The storm's ability to encircle the planet and persist for months is shown in detail, demonstrating the dynamic and ever-changing nature of Saturn's atmosphere. The simulations also explore the long-lived vortices in Saturn's mid-latitudes. These large-scale storms are shown interacting with surrounding cloud bands, influencing weather patterns across vast areas of the planet. By modeling different atmospheric conditions, scientists can simulate how changes in temperature, wind speed, and atmospheric composition affect storm formation and behavior. These visualizations help refine our understanding of Saturn's meteorology. Simulations of lightning storms provide a detailed look at the electrical activity within Saturn's atmosphere. The distribution and intensity of lightning strikes are mapped, offering a clear picture of the storm's energy dynamics. The simulations also depict the vertical structure of Saturn's storms. By showing the depth and layers within the atmosphere, these visualizations reveal how storms extend deep into the planet and interact with various atmospheric layers. Another key aspect of the simulations is the seasonal changes in Saturn's atmosphere. Visualizations show how storms evolve with the planet's long seasons, influenced by varying solar radiation and atmospheric dynamics. These visual simulations are crucial for understanding the complexities of Saturn's storms. They provide a comprehensive view of the forces shaping the planet's weather, enhancing our knowledge of gas giant atmospheres and informing future exploration. Ring rain is a fascinating phenomenon where particles from Saturn's rings fall into the planet's atmosphere. This occurs when micrometeoroids collide with the rings, knocking ice and dust particles into the upper atmosphere. These particles are influenced by Saturn's magnetic field, which guides them along magnetic field lines down into the planet. This interaction creates a complex interplay between the rings and the atmosphere. As the particles enter the atmosphere, they can react chemically with the atmospheric gases. This process can lead to changes in the composition of Saturn's upper atmosphere, affecting its overall chemical balance. Ring rain also contributes to the planet's weather by influencing cloud formation. The particles can act as nuclei around which clouds can form, potentially altering cloud cover and atmospheric dynamics. The influx of material from the rings can also affect the thermal structure of the atmosphere. By absorbing and scattering sunlight, these particles can impact the temperature distribution in Saturn's upper layers. Saturn's auroras, which are influenced by interactions with the rings, are also affected by ring rain. The falling particles can enhance auroral activity by increasing the amount of material available to interact with the magnetic field. Observations from the Cassini spacecraft provided detailed insights into ring rain. Instruments detected the composition and distribution of the particles, offering a clearer picture of how this process operates. Ring rain can vary in intensity based on the position and density of the rings. During certain periods, more particles can be dislodged and rain down, leading to temporary changes in atmospheric conditions. The continuous influx of particles from the rings means that Saturn's atmosphere is constantly being polluted with new material. This process contributes to the dynamic and ever-changing nature of the planet's weather systems. Understanding ring rain helps scientists learn about the life cycle of Saturn's rings. Over time, this process can lead to the gradual erosion of the rings as more material falls into the planet. The chemical interactions between the ring particles and atmospheric gases can lead to the formation of new compounds. These compounds can influence the color and reflectivity of Saturn's atmosphere. The distribution of ring rain is not uniform. Different regions of the planet can experience varying levels of particle influx, leading to localized changes in weather and atmospheric composition. The interaction between ring rain and Saturn's magnetic field can also generate radio emissions. These emissions provide additional data on the strength and structure of the planet's magnetic environment. Ring rain highlights the interconnected nature of Saturn's rings and atmosphere. The continuous exchange of material between the two systems showcases the complexity of planetary weather processes. Studying ring rain and its effects on Saturn's weather helps scientists understand the broader dynamics of gas giant planets. These insights can be applied to other planets with ring systems, enhancing our knowledge of how rings influence planetary atmospheres across the solar system. Uranus has a unique atmosphere primarily composed of hydrogen and helium, with a substantial amount of methane giving it a blue-green hue. This methane absorbs red light from the sun and reflects blue light, creating its distinct color. The atmosphere of Uranus is remarkably cold, with temperatures dropping as low as -224 degrees Celsius. This makes it one of the coldest planets in our solar system, influenced by its distance from the sun and lack of internal heat. Clouds in Uranus's atmosphere are composed of water, ammonia, and methane ice. These clouds form at different altitudes, creating a layered structure that contributes to the planet's weather patterns. Despite its calm appearance, Uranus experiences strong winds that can reach speeds of up to 560 miles per hour. These winds contribute to the planet's weather systems and atmospheric dynamics. Neptune's atmosphere is similar to Uranus, composed mainly of hydrogen, helium, and methane. The presence of methane gives Neptune its striking blue color, even more vivid than Uranus. Neptune's atmosphere is more active, with visible storm systems and dynamic weather patterns. The planet experiences the fastest winds in the solar system, reaching speeds of up to 1,200 miles per hour. One of Neptune's most prominent features is the Great Dark Spot, a massive storm comparable to Jupiter's Great Red Spot. This storm highlights the turbulent nature of Neptune's atmosphere. Neptune's atmosphere is also extremely cold, with temperatures around -214 degrees Celsius. However, it emits more heat than it receives from the sun, suggesting an internal heat source driving its dynamic weather. The clouds on Neptune are primarily composed of methane ice, with higher clouds possibly containing hydrogen sulfide. These clouds form intricate and rapidly changing weather patterns. Both Uranus and Neptune have unique magnetic fields that are tilted relative to their rotational axes. This unusual orientation influences their atmospheric behavior and contributes to their complex weather systems. The atmospheres of these two ice giants also contain haze layers, which can affect their overall appearance and cloud dynamics. These hazes are formed from photochemical reactions driven by sunlight. Observations from spacecraft like Voyager 2 and the Hubble Space Telescope have provided valuable data on the atmospheres of Uranus and Neptune. These missions revealed detailed images and measurements of the planet's atmospheric conditions. Understanding the atmospheres of Uranus and Neptune helps scientists learn more about the formation and evolution of the outer planets. These ice giants offer clues about the processes that shape planetary atmospheres in our solar system. Studying these distant atmospheres also provides insights into exoplanets with similar compositions. By comparing Uranus and Neptune to exoplanets, scientists can refine their models of atmospheric dynamics beyond our solar system. The continued exploration and observation of Uranus and Neptune are crucial for advancing our knowledge of planetary science. These ice giants hold many secrets that can deepen our understanding of atmospheric processes and the diversity of planets in the universe. The high-speed winds on Uranus are quite remarkable, reaching up to 560 miles per hour. These winds are most intense at mid-latitudes and are believed to be driven by complex interactions between the planet's atmosphere and its internal heat. Uranus's winds blow in the direction of the planet's rotation, creating a pattern of eastward and westward jet streams. These jet streams influence the overall weather patterns and contribute to the formation of cloud bands. At the equator, Uranus's winds tend to be weaker, while they gain strength towards the poles. This distribution creates a unique atmospheric dynamic that is still not fully understood by scientists. The cold temperatures on Uranus, combined with its axial tilt, contribute to the intensity and variability of its winds. Seasonal changes due to its extreme tilt cause significant variations in wind patterns and atmospheric circulation. Neptune, on the other hand, exhibits the fastest winds in the solar system, reaching speeds of up to 1,200 miles per hour. These supersonic winds are driven by the planet's internal heat and its dynamic atmosphere. Neptune's winds are most prominent in its equatorial regions, where they form powerful jet streams. These jet streams create bands of clouds that move at different speeds, adding to the planet's turbulent appearance. The Great Dark Spot on Neptune is a clear example of these intense winds in action. This massive storm is driven by high-speed winds, which contribute to its rotation and stability over time. Neptune's winds also play a crucial role in the planet's overall weather system, driving the formation and movement of storms and cloud features. The rapid wind speeds lead to frequent and dramatic changes in the atmosphere. Both Uranus and Neptune have wind patterns that are influenced by their unique magnetic fields. The tilt and orientation of these magnetic fields affect how winds circulate and interact with the planetary atmosphere. The presence of methane in both planets' atmospheres also affects wind behavior. Methane's ability to absorb solar energy influences temperature gradients, which in turn drive wind speeds and patterns. Understanding the winds on Uranus and Neptune provides valuable insights into the dynamics of gas giant atmospheres. These high-speed winds highlight the complexity of atmospheric processes on these distant planets. Studying these winds helps scientists learn more about the internal heat sources of Uranus and Neptune. The energy driving these winds likely comes from deep within the planets, contributing to their overall atmospheric activity. Observations from spacecraft and telescopes have been crucial in measuring and understanding these winds. Instruments on missions like Voyager 2 and the Hubble Space Telescope have provided detailed data on wind speeds and patterns. Comparing the winds on Uranus and Neptune with those on other gas giants like Jupiter and Saturn helps scientists build comprehensive models of planetary atmospheres. These comparisons reveal both similarities and unique characteristics. Continued research into the high-speed winds on Uranus and Neptune will enhance our understanding of atmospheric dynamics. These winds are key to unlocking the mysteries of these ice giants and the broader processes that govern planetary weather systems. Historical observations of Uranus and Neptune began with telescopic studies in the 18th and 19th centuries. Uranus was discovered by William Herschel in 1781, while Neptune was discovered by Johann Galle in 1846, based on predictions by Urbain Le Verrier and John Couch Adams. Early observations focused on the basic characteristics of these planets, including their sizes, orbits, and colors. The limited technology of the time provided only faint glimpses of their atmospheres and weather patterns. With the advent of more powerful telescopes in the 20th century, astronomers began to observe more details about Uranus and Neptune. These observations revealed the presence of methane in their atmospheres and hinted at dynamic weather systems. The Voyager 2 spacecraft provided the first close-up images and detailed data of Uranus in 1986 and Neptune in 1989. These flybys revolutionized our understanding of both planets, revealing their complex atmospheres, rings, and moons. Voyager 2's observations of Uranus showed a relatively bland atmosphere with few visible features, but it detected strong winds and temperature variations. The spacecraft also discovered 11 new moons and a detailed ring system. When Voyager 2 flew by Neptune, it captured images of the Great Dark Spot and other storm systems. The spacecraft recorded the fastest winds in the solar system and provided a wealth of data on Neptune's magnetic field and internal heat. In the years following the Voyager missions, ground-based telescopes and the Hubble Space Telescope have continued to observe Uranus and Neptune. Advances in technology have allowed for more detailed images and measurements. Hubble's observations have revealed seasonal changes on Uranus, including variations in cloud cover and atmospheric dynamics as the planet orbits the Sun. These changes are influenced by Uranus's extreme axial tilt, which causes unique seasonal variations. For Neptune, Hubble has observed changes in the Great Dark Spot and the appearance of new storm systems. These observations provide insights into the planet's atmospheric dynamics and the life cycle of its weather patterns. The Keck Observatory and other ground-based facilities have used adaptive optics to capture high-resolution images of Uranus and Neptune. These observations have revealed intricate details of the planet's atmospheres and rings. Current observations continue to monitor both planets for changes and new phenomena. The discovery of transient features, such as new storms or variations in wind patterns, helps scientists refine their models of planetary atmospheres. Planned future missions, such as proposed orbiter missions to Uranus or Neptune, aim to provide even more detailed observations. These missions would study the planet's atmospheres, magnetic fields, and potential subsurface oceans. Continued monitoring by telescopes and spacecraft will enhance our understanding of the dynamic processes at work on Uranus and Neptune. These observations are crucial for understanding the broader context of gas giant planets in our solar system. Historical and current observations of Uranus and Neptune contribute to our knowledge of planetary formation and evolution. These ice giants offer unique insights into the processes that shape planets, both in our solar system and beyond. As technology advances, the ability to observe and study Uranus and Neptune will only improve. Future discoveries will build on the foundation laid by past observations, deepening our understanding of these distant and intriguing worlds. Neptune's dark spots are some of the most intriguing and dynamic features in the solar system. These storms are similar to Jupiter's Great Red Spot, but differ in their size, lifespan, and behavior. The most famous of these is the Great Dark Spot, first observed by Voyager 2 in 1989. This massive storm was about the size of Earth, showcasing powerful winds and complex atmospheric interactions. The Great Dark Spot was located in Neptune's southern hemisphere, with winds reaching up to 1,500 miles per hour. These high-speed winds make Neptune's dark spots some of the most violent storms in the solar system. Unlike Jupiter's Great Red Spot, which has persisted for centuries, Neptune's dark spots appear to be more transient. The great dark spot observed by Voyager 2 had disappeared by the time the Hubble Space Telescope observed Neptune 5 years later. The transient nature of Neptune's dark spots suggests that they form and dissipate relatively quickly, influenced by the planet's dynamic and turbulent atmosphere. New spots have been observed to appear in different locations and sizes over the years. In 1994, Hubble discovered another storm, often referred to as the Northern Great Dark Spot. This storm was similar in size and characteristics to the original Great Dark Spot, but located in the Northern Hemisphere. More recently, Hubble observations in 2018 revealed a new dark spot in the Northern Hemisphere, indicating that these storms continue to be a recurring feature of Neptune's weather. This dark spot, along with others, provides valuable data on the planet's atmospheric processes. The dark spots are typically accompanied by bright white clouds that form due to upwelling gas that cools and condenses into methane ice crystals. These companion clouds provide additional visual markers for studying the storms. The mechanisms behind the formation of Neptune's dark spots are still not fully understood. They are believed to be high-pressure systems, similar to Earth's anticyclones, but on a much larger and more intense scale. Studies of these storms suggest that they may be influenced by Neptune's internal heat, which drives convection and creates conditions favorable for storm formation. The planet's rapid rotation also plays a role in shaping and sustaining these storms. The dark spots provide a natural laboratory for understanding atmospheric dynamics in extreme conditions. By studying these storms, scientists gain insights into fluid dynamics, storm formation, and the behavior of atmospheres under different thermal and chemical conditions. Observations of Neptune's dark spots also contribute to comparative planetology. By comparing these storms to those on other gas giants like Jupiter and Saturn, scientists can develop broader theories about storm dynamics in the solar system. Future missions to Neptune could provide even more detailed data on these dark spots. Instruments capable of observing the planet's atmosphere in various wavelengths would offer a deeper understanding of the composition and behavior of these storms. Neptune's dark spots are a testament to the planet's dynamic and ever-changing atmosphere. They highlight the complex interplay between internal and external forces, shaping the weather on this distant ice giant. As we continue to explore and study Neptune, the dark spots will remain a focal point for understanding the planet's atmospheric dynamics. These storms offer a window into the powerful and mysterious processes at work in the outer solar system. Neptune's dark spots and Jupiter's Great Red Spot are both massive storm systems, but they exhibit key differences in size, lifespan, and dynamics. Jupiter's Great Red Spot is significantly larger, measuring about twice the diameter of Earth, while Neptune's dark spots are roughly the size of our planet. The Great Red Spot has been a persistent feature for at least 400 years, showcasing a remarkable stability. In contrast, Neptune's dark spots are more transient, appearing and disappearing over the course of a few years. Wind speeds in the Great Red Spot reach up to 400 miles per hour, whereas Neptune's dark spots experience even higher wind speeds, up to 1,500 miles per hour. These intense winds contribute to the extreme weather conditions on both planets. The Great Red Spot is a high-pressure system with anticyclonic rotation, meaning it rotates counterclockwise in the southern hemisphere. Similarly, Neptune's dark spots are also high-pressure systems with anticyclonic characteristics. The coloration of these storms differs significantly. The Great Red Spot's distinctive red hue is thought to be due to the presence of complex organic molecules, red phosphorus, or other chemicals that react with ultraviolet light. Neptune's dark spots, on the other hand, appear dark blue, likely due to the deeper atmospheric layers being visible through methane absorption. Both types of storms are accompanied by bright clouds. On Jupiter, these are ammonia ice clouds, while on Neptune, the bright clouds are composed of methane ice crystals that form as the upwelling gases cool and condense. The energy sources driving these storms differ. Jupiter's Great Red Spot is powered by the planet's immense internal heat, which drives convective currents. Neptune, while also emitting more heat than it receives from the Sun, has a less understood internal heat source, but this energy still plays a crucial role in storm formation. The longevity of the Great Red Spot allows for continuous observation and study, providing a wealth of data on its structure and behavior. In contrast, the transient nature of Neptune's dark spots makes them more challenging to study, as they can change or disappear relatively quickly. Both storm systems provide valuable insights into planetary atmospheres and weather patterns. Studying these storms helps scientists understand fluid dynamics, atmospheric chemistry, and the effects of rotation on planetary weather. The Great Red Spot's stability and size make it a dominant feature of Jupiter's atmosphere, influencing weather patterns across the planet. Neptune's dark spots, though less enduring, are still significant in shaping local weather dynamics. Comparative studies of these storm systems enhance our understanding of atmospheric processes. By examining the similarities and differences between Jupiter and Neptune storms, scientists can develop more comprehensive models of gas giant atmospheres. The visual appearances of these storms provide clues about their composition and the atmospheric layers involved. The red and blue hues indicate different chemical compositions and processes at work within the planet's atmospheres. The dynamics of these storms are influenced by the planet's rapid rotations. Both Jupiter and Neptune have short rotational periods, contributing to strong Coriolis effects that shape their storm systems. The study of these giant storms has implications for understanding exoplanetary atmospheres. Observations of similar storm systems on distant gas giants can be informed by the knowledge gained from Jupiter and Neptune. As exploration continues, future missions and telescopic observations will further unravel the mysteries of these colossal storms. Understanding the forces that sustain and drive these weather systems will provide deeper insights into the complex and dynamic nature of gas giant planets. Seasonal changes on Uranus and Neptune are profound due to their extreme axial tilts and long orbital periods. Uranus, with an axial tilt of 98 degrees, experiences extreme seasonal variations, with each pole getting around 42 years of continuous sunlight followed by 42 years of darkness. These long seasons cause significant atmospheric changes. When a hemisphere is tilted toward the sun, it heats up, leading to increased storm activity and altered wind patterns. As the planet moves along its orbit, these patterns shift dramatically. Neptune's axial tilt is similar to Earth's, about 28 degrees, which results in more moderate seasonal changes. However, given its long orbital period of 165 years, each season lasts over 40 Earth years, still leading to noticeable atmospheric variations. During Neptune's southern summer, the planet's atmosphere becomes more active, with increased storm activity and higher wind speeds. Observations have shown that storm systems, including dark spots, are more prevalent during these warmer periods. The extreme weather patterns on these planets are driven by both external and internal factors. Solar radiation affects the outer atmospheric layers, while internal heat plays a significant role in driving convective storms and wind patterns. On Uranus, the contrast between its seasons is stark. The winter hemisphere is shrouded in darkness, leading to cooler temperatures and calmer weather. As the planet approaches equinox, the atmosphere becomes more turbulent, with increasing storm activity and wind speeds. Neptune's extreme weather includes powerful storms like the Great Dark Spot, which are influenced by the planet's internal heat. These storms can form and dissipate over a few years, reflecting the dynamic nature of Neptune's atmosphere. Seasonal changes also affect the visibility and behavior of clouds on both planets. For instance, the bright methane clouds on Neptune become more prominent during the summer months, when increased solar heating causes more vigorous atmospheric activity. The axial tilt of Uranus results in unique weather phenomena not seen on any other planet. During its equinox, when the sun is directly over the equator, the planet experiences rapid changes in atmospheric dynamics, leading to intense and unpredictable weather patterns. Neptune's seasons bring about shifts in the planet's bands and zones. These changes in atmospheric circulation can lead to the formation of new storm systems and the disappearance of existing ones, showcasing the planet's ever-changing weather. The long duration of seasons on both Uranus and Neptune means that scientists must observe these planets over many years to understand their full atmospheric cycles. This long-term observation is crucial for identifying patterns and predicting future weather behavior. The extreme axial tilt of Uranus can lead to unusual weather effects, such as the formation of polar vortices during the summer and winter solstices. These vortices can influence global atmospheric circulation and contribute to the planet's complex weather patterns. Neptune's rapid winds and frequent storms during its summer are indicative of the planet's dynamic atmosphere. The increased solar heating during this period enhances convective currents, leading to more energetic weather systems. Seasonal changes on Uranus and Neptune are not just limited to atmospheric phenomena. These changes also affect the planet's magnetic fields and ring systems, further influencing their overall environmental conditions. Understanding the seasonal changes and extreme weather patterns on these distant ice giants provides valuable insights into the dynamics of planetary atmospheres. This knowledge helps scientists compare and contrast with other planets in our solar system and beyond, enriching our understanding of the universe. On Titan, Saturn's largest moon, methane lakes and rain create a weather system that is both alien and fascinating. These lakes are primarily located near the moon's poles and are composed of liquid methane and ethane. Methane rain on Titan is part of a cycle similar to Earth's water cycle. Methane evaporates from the surface, forms clouds, and falls back as rain, creating rivers, lakes, and seas. The presence of methane lakes and rain on Titan was confirmed by the Cassini-Huygens mission. Radar images revealed large, dark areas near the poles, indicating the presence of stable liquid bodies. Titan's thick atmosphere, composed mainly of nitrogen with a small amount of methane, allows for the existence of liquid methane on its surface. The surface pressure is high enough and the temperature is low enough for methane to remain liquid. Rain on Titan is slow and gentle compared to Earth. The lower gravity and thicker atmosphere cause methane raindrops to fall more slowly, creating a different kind of precipitation experience. The lakes and seas on Titan vary in size, with some larger than Earth's Great Lakes. The largest sea, Kraken Mare, spans over 1,000 kilometers, showcasing the vast scale of Titan's liquid bodies. Seasonal changes on Titan affect the distribution of methane lakes and rainfall. During the moon's summer, methane evaporation increases, leading to more cloud formation and potential rainstorms. Methane lakes and rain contribute to Titan's dynamic surface. River channels carved by flowing methane and ethane show that liquid erosion shapes the landscape, much like water shapes Earth's terrain. The interaction between Titan's surface and atmosphere creates intriguing weather patterns. Methane clouds can form quickly and dissipate just as fast, leading to sudden rain showers and changing surface conditions. The existence of liquid methane on Titan raises the possibility of prebiotic or even biotic processes. Although the chemistry would be vastly different from Earth's, the presence of liquid, an essential ingredient for life, makes Titan a key target for astrobiological studies. Understanding Titan's methane cycle helps scientists compare and contrast it with Earth's water cycle. These comparisons provide insights into the fundamental processes that govern planetary weather systems. Methane rain on Titan can fill lakes and seas, but it can also cause seasonal flooding. As the methane level in the lakes rises, it can overflow into surrounding areas, creating temporary rivers and altering the landscape. The Cassini spacecraft provided detailed data on Titan's lakes, revealing their depth and composition. Some lakes are several hundred meters deep, with smooth reflective surfaces indicating calm, stable liquid bodies. Titan's methane cycle is driven by the low temperatures in the outer solar system. With surface temperatures around -180 degrees Celsius, methane can exist in liquid form, creating a unique and stable hydrological cycle. The study of methane lakes and rain on Titan expands our understanding of planetary science and the diversity of weather systems in the solar system. These discoveries inspire further exploration and the search for similar phenomena on other moons and planets. Titan's surface is a complex landscape, shaped by both geological and atmospheric processes. It is composed primarily of water ice and rocky material, covered by a thick layer of organic compounds. The atmosphere of Titan is dense and hazy, composed mainly of nitrogen, with significant amounts of methane and hydrogen. This thick atmosphere creates a surface pressure 1.5 times that of Earth, allowing liquid methane to exist on the surface. The temperature on Titan's surface is extremely cold, averaging around -180 degrees Celsius. These low temperatures keep methane and ethane in liquid form, creating rivers, lakes, and seas. Titan's haze is caused by complex organic molecules known as tholins, which form in the upper atmosphere and settle onto the surface. This haze scatters sunlight, giving Titan its characteristic orange hue. The thick atmosphere and hazy conditions mean that sunlight on Titan is diffused, creating a dim, twilight-like environment even during the day. This limited light affects surface temperatures and weather patterns. Winds on Titan are generally mild due to the thick atmosphere, but they can still shape the surface, creating dunes and transporting sediment. These winds are driven by temperature gradients and Titan's rotation. The surface features of Titan include vast dune fields, likely composed of hydrocarbon grains, and icy plains. The dunes are similar in appearance to those found in deserts on Earth, but they are formed from different materials. Impact craters are relatively rare on Titan, indicating a geologically young surface. Erosion and deposition from methane rain and rivers continually reshape the landscape, erasing older craters. Cryovolcanoes, or ice volcanoes, are thought to exist on Titan, spewing water and ammonia instead of molten rock. These eruptions contribute to the surface composition and may play a role in the methane cycle. The dense atmosphere allows for the existence of stable liquid bodies on Titan's surface, unique among known moons in the solar system. The interaction between the atmosphere and surface creates dynamic weather patterns, including methane rainstorms. Methane clouds form in the lower atmosphere, driven by Titan's weather systems. These clouds can precipitate as methane rain, contributing to the hydrological cycle and filling lakes and rivers. The interaction between the surface and atmosphere on Titan is complex, with seasonal variations affecting weather patterns. As Titan orbits Saturn, changing sunlight conditions drive atmospheric dynamics and surface processes. The thick atmosphere provides significant insulation, keeping Titan's surface relatively stable in temperature despite the weak sunlight. This insulation also creates a greenhouse effect, trapping heat and allowing liquid methane to persist. The haze and clouds in Titan's atmosphere scatter light, creating stunning visual effects and complex patterns. These atmospheric phenomena are key to understanding the weather and climate on this distant moon. Studying Titan's surface and atmospheric conditions provides valuable insights into the processes that shape planetary bodies. The unique environment of Titan, with its dense atmosphere and methane cycle, offers a fascinating parallel to Earth and enriches our understanding of planetary science. Volcanic activity on Io, one of Jupiter's moons, is the most intense in the solar system. Io's surface is dotted with hundreds of volcanoes, some of which are active and erupting continuously. These volcanic eruptions are driven by the intense tidal forces exerted by Jupiter and its other large moons. The gravitational interactions create immense internal friction and heat, leading to volcanic activity. Io's volcanoes spew out sulfur and sulfur dioxide, creating large, colorful deposits on the surface. These materials give Io its distinctive yellow, orange, and red appearance. One of the most prominent volcanic features on Io is Loki Patera, a massive volcanic depression that undergoes periodic eruptions. It is considered one of the most powerful volcanoes in the solar system. The volcanic plumes on Io can reach astonishing heights, sometimes extending up to 300 miles above the surface. These plumes are visible from space and contribute to Io's thin atmosphere. Sulfur dioxide plumes are a key feature of Io's volcanism. When the sulfur dioxide is released, it condenses to form frost and snow, which can cover large areas of the surface. The continuous volcanic activity constantly reshapes Io's surface, covering older features with new deposits. This makes Io one of the most geologically dynamic bodies in the solar system. The energy driving Io's volcanic activity is immense. The tidal heating generates more than enough heat to keep Io's interior partially molten, fueling ongoing eruptions. These volcanic processes have a significant impact on Io's atmosphere. The sulfur dioxide released into the atmosphere can be ionized by Jupiter's magnetic field, creating a plasma torus around the moon. The plasma torus is a ring of charged particles that orbits Jupiter along with Io. It interacts with Jupiter's magnetosphere and contributes to the planet's auroras. The intense volcanic activity on Io also affects its surrounding environment. The material ejected by the volcanoes can escape Io's gravity and become part of Jupiter's magnetosphere. This volcanic activity provides a natural laboratory for studying extreme geologic processes. The constant resurfacing and active volcanism on Io offer insights into the internal dynamics of rocky bodies. Observations of Io's volcanic activity have been made by various spacecraft, including Voyager, Galileo, and the Juno mission. These missions have provided detailed images and data on the moon's geology and volcanic processes. Io's volcanism is a stark contrast to the more familiar tectonic activity seen on Earth. Understanding the mechanisms driving Io's intense volcanic activity helps scientists learn more about the diversity of geologic processes in the solar system. The study of volcanic activity and sulfur dioxide plumes on Io enhances our knowledge of how moons and planets evolve. These insights contribute to our broader understanding of planetary science and the dynamic nature of celestial bodies. Io's surface conditions are extreme, shaped by continuous volcanic activity and intense tidal forces. The surface is a mosaic of colorful deposits, primarily composed of sulfur and sulfur dioxide frost. The temperatures on Io vary drastically. While the average surface temperature is about -202 degrees Fahrenheit, volcanic hotspots can reach up to 2,500 degrees Fahrenheit, creating a stark contrast. These hotspots are visible in infrared images, showing the intense heat from active volcanic regions. The energy from these hotspots drives much of Io's surface activity and contributes to its dynamic landscape. Io's surface is also covered with vast lava flows, some extending hundreds of miles. These flows create smooth plains and contribute to the constant resurfacing of the moon, burying older features beneath new deposits. Impact craters are rare on Io, indicating a geologically young surface. The continuous volcanic activity quickly erases craters, maintaining a constantly renewing landscape. The intense tidal forces exerted by Jupiter and its neighboring moons create significant stress on Io's crust. This stress leads to frequent seismic activity and contributes to the formation of cracks and fissures. These fissures can release large amounts of sulfur dioxide gas, which then condenses on the surface. The interaction between the gas and the surface materials creates a variety of sulfur compounds, adding to Io's colorful appearance. The surface of Io is also dotted with mountains, some reaching heights of over 10 miles. These mountains are thought to be formed by tectonic processes, driven by the same tidal forces that cause volcanic activity. Erosion on Io is primarily driven by volcanic activity rather than weathering, as the moon lacks a substantial atmosphere. The surface changes are rapid and dramatic, shaped by eruptions and lava flows. The thin atmosphere of Io is primarily composed of sulfur dioxide, created by volcanic outgassing. This atmosphere is transient, with the gas continuously being lost to space and replenished by volcanic eruptions. Io's volcanic plumes deposit sulfur dioxide and other materials onto the surface, creating layered deposits. These plumes can also affect the moon's immediate environment, including its interaction with Jupiter's magnetosphere. The impacts of Io's surface conditions extend beyond the moon itself. The material ejected by its volcanoes contributes to the plasma torus around Jupiter, influencing the planet's magnetosphere and radiation belts. The intense volcanic activity on Io makes it a fascinating subject for scientific study. Understanding Io's surface conditions and impacts provides insights into the geologic processes that can occur on other volcanic moons and planets. The continuous resurfacing of Io offers a unique opportunity to study how volcanic activity can shape a planetary body over time. This knowledge can be applied to understanding similar processes on Earth and other celestial bodies. By studying Io, scientists gain a better understanding of how tidal forces and volcanic activity interact to create dynamic and evolving surfaces. These insights contribute to our broader knowledge of planetary geology and the diverse processes that shape the moons and planets in our solar system. We've explored some of the most dangerous and extreme weather events in the solar system, each showcasing the incredible power and variety of atmospheric phenomena beyond Earth. On Venus, the runaway greenhouse effect creates surface temperatures hot enough to melt lead, with crushing atmospheric pressure and sulfuric acid clouds that perpetually rain down but evaporate before reaching the surface. Mars hosts massive dust storms that can cover the entire planet, turning day into night and lasting for months. These storms significantly impact future exploration missions by affecting solar power generation and visibility. Jupiter's Great Red Spot is a colossal storm that has raged for centuries, with wind speeds reaching 400 miles per hour. This massive storm could easily engulf Earth and is a testament to Jupiter's turbulent atmosphere. Saturn's hexagon storm at the North Pole is a unique, six-sided jet stream structure that remains stable over time. This geometric wonder, combined with powerful polar vortexes, showcases Saturn's dynamic weather. Titan's methane lakes and rain create an alien yet familiar weather system, with a methane cycle analogous to Earth's water cycle. Methane rain, rivers and seas shape Titan's surface in ways that are both exotic and similar to our own planet. Io's volcanic activity is the most intense in the solar system, with sulfur dioxide plumes reaching hundreds of miles above the surface. The continuous eruptions and high temperatures create a constantly changing and hostile environment. Neptune's dark spots are massive storms, similar to Jupiter's Great Red Spot, but more transient. These storms reach wind speeds up to 1,500 miles per hour, making Neptune's atmosphere incredibly dynamic and violent. Comparisons between these storms and those on Earth highlight the differences in scale and intensity. While Earth experiences powerful hurricanes and tornadoes, they pale in comparison to the vast and long-lasting storms on other planets. Seasonal changes on Uranus and Neptune lead to significant atmospheric variations. Uranus's extreme axial tilt causes dramatic seasonal shifts, while Neptune's long seasons drive changes in storm activity and atmospheric dynamics. Methane lakes and rain on Titan provide a unique perspective on extraterrestrial weather systems. The presence of liquid methane and ethane shapes Titan's landscape and offers clues about the potential for life in extreme environments. Sulfur dioxide plumes on Io contribute to a thin, transient atmosphere and interact with Jupiter's magnetosphere. The continuous volcanic activity makes Io a key subject for understanding geologic and atmospheric processes on other worlds. The high-speed winds on both Uranus and Neptune showcase the power of atmospheric circulation in the outer solar system. These winds drive complex weather patterns and contribute to the formation of massive storm systems. Visual simulations and observations from missions like Voyager and Cassini have been crucial in understanding these extreme weather events. These missions provide detailed data and stunning imagery that reveal the dynamic nature of these distant worlds. Studying these dangerous weather events helps scientists learn more about the fundamental processes that shape planetary atmospheres. This knowledge enhances our understanding of weather and climate across the solar system and informs the search for habitable conditions on other planets. The variety and intensity of weather events discussed underscore the diversity of atmospheric phenomena in our solar system. From scorching heat to icy winds, each planet and moon offers a unique glimpse into the powerful forces at work beyond Earth. Ongoing research and missions are crucial for expanding our understanding of the solar system's weather phenomena. Each mission provides new data that can reshape our knowledge and offer fresh insights into planetary science. Studying extreme weather events on other planets helps us learn more about Earth's own atmospheric dynamics. By comparing these alien weather systems to our own, we can better understand the fundamental processes that drive climate and weather. Missions like Voyager, Cassini, and Juno have revolutionized our understanding of gas giants and their moons. These spacecraft have provided detailed images and measurements, revealing the complexities of planetary atmospheres and surfaces. Future missions to the outer planets and their moons will continue to unveil new discoveries. Planned missions to Uranus and Neptune, for example, aim to explore these ice giants in unprecedented detail, shedding light on their atmospheres, magnetic fields, and potential subsurface oceans. Robotic landers and rovers are essential for studying surface conditions up close. Missions like the Mars rovers and the planned Dragonfly mission to Titan offer the opportunity to directly analyze surface materials and atmospheric interactions. Satellites and space telescopes, such as the Hubble Space Telescope and the upcoming James Webb Space Telescope, provide continuous monitoring of distant planets. These observations are critical for tracking changes and identifying new weather patterns. Research into planetary weather helps us prepare for future human exploration. Understanding the extreme conditions on other worlds allows us to design better spacecraft, habitats, and survival strategies for astronauts. Climate models developed from studying other planets can improve our predictions for Earth's climate. Insights gained from these models help us anticipate and mitigate the impacts of climate change on our own planet. International collaboration in space exploration brings together the best minds and technologies from around the world. By working together, we can achieve more comprehensive and ambitious missions, enhancing our collective knowledge of the universe. Educational outreach and public engagement are vital aspects of space missions. Sharing discoveries with the public inspires the next generation of scientists and fosters a greater appreciation for the wonders of our solar system. Continuous research also informs the search for extraterrestrial life. Understanding the conditions on other planets and moons helps us identify environments where life might exist, guiding future missions in the search for life beyond Earth. Innovations in space technology, driven by these missions, often have applications here on Earth. Advances in robotics, materials science, and data analysis benefit a wide range of industries and improve our daily lives. The quest to understand the solar system's weather extends to exoplanets as well. By studying planets around other stars, we can place our own solar system in a broader context and learn about the diversity of planetary environments in the galaxy. Ongoing missions contribute to the legacy of exploration and discovery that began with the earliest astronomers. Each new finding builds on the work of those who came before, creating a richer and more detailed picture of the universe. The importance of ongoing research and missions cannot be overstated. As we continue to explore and study the solar system, we unlock new mysteries and expand our understanding of the cosmos, driving human curiosity and innovation forward. As we've journeyed through the solar system, we've encountered the most extreme and fascinating weather phenomena. From the runaway greenhouse effect on Venus to the methane lakes on Titan, each planet and moon offers unique insights into the powerful forces at play in our universe. These explorations highlight the importance of ongoing research and missions. By studying these distant worlds, we deepen our understanding of atmospheric dynamics and geological processes, enriching our knowledge of the cosmos. The data collected from missions like Voyager, Cassini, and Juno have transformed our understanding of planetary weather. Future missions will continue this legacy, uncovering new mysteries and expanding our horizons. The insights gained from studying other planets also enhance our understanding of Earth's climate. By comparing and contrasting weather systems, we can develop better models and strategies to address climate change here at home. Space exploration inspires us to push the boundaries of what is possible. The challenges faced and overcome by missions to the outer planets drive technological advancements that benefit all of humanity. The quest to understand the universe is a shared human endeavor. International collaboration in space exploration unites us in our pursuit of knowledge, fostering a spirit of cooperation and mutual respect. As we look to the future, the possibilities for discovery are endless. New technologies and innovative missions will continue to reveal the wonders of our solar system and beyond. Public engagement and education are crucial in this journey. By sharing our discoveries, we inspire future generations to dream big and pursue careers in science, technology, engineering, and mathematics. The search for extraterrestrial life remains one of the most compelling aspects of space exploration. Understanding the conditions that support life on other planets and moons guides our search and fuels our curiosity. Every mission, every discovery, adds a piece to the puzzle of our universe. The more we learn, the more we realize there is still so much to explore and understand. The beauty and complexity of the solar system remind us of the interconnectedness of all things. Each planet and moon, with its unique characteristics, contributes to the rich tapestry of the cosmos. As we continue our explorations, we must also consider the preservation and protection of these distant worlds. Responsible exploration ensures that future generations can continue to learn from and appreciate the wonders of the universe. The pursuit of knowledge is a journey without end. With each mission, we take another step forward, driven by curiosity and the desire to understand our place in the universe. Thank you for joining us on this incredible journey through the most dangerous weather in the solar system. Together, we will continue to explore, discover, and marvel at the wonders of our cosmic neighborhood. The adventure of space exploration is just beginning. Stay curious, stay inspired, and keep looking up at the stars. The universe is waiting to be explored. Thank you for joining us on this incredible journey through the solar system's most extreme weather. If you enjoyed this exploration, we invite you to subscribe to our channel for more fascinating content about the universe. Don't forget to hit the notification bell so you never miss an update. We have a lot more exciting videos planned, covering everything from black holes to the search for extraterrestrial life. We'd love to hear your thoughts on today's video. Leave a comment below and let us know which weather phenomenon amazed you the most. If you have any questions or topics you'd like us to cover in future videos, feel free to share them in the comments. Your feedback helps us create content that you find interesting and informative. Share this video with your friends and family who love space and science. Let's spread the wonder of the cosmos and inspire curiosity in others. Follow us on social media for behind-the-scenes content, updates on upcoming videos, and additional space facts and news. You'll find links in the description below. Join our community of space enthusiasts by participating in our discussion forums. It's a great place to connect with like-minded individuals and dive deeper into the topics we explore. Consider supporting us on Patreon. Your support helps us continue to produce high-quality educational content and allows us to explore even more fascinating subjects. Check out our merch store for exclusive space-themed merchandise. Wearing our gear is a great way to show your passion for the cosmos and support our channel. Sign up for our newsletter to receive the latest news and updates from our channel directly in your inbox. You'll be the first to know about new videos and special events. Attend our live Q&A sessions, where we answer your questions in real time and discuss the latest discoveries in space science. These sessions are a great way to engage with our content on a deeper level. Download our free ebook on the solar system's wonders, packed with additional information and stunning images. It's a perfect companion to our videos and a great resource for learning more. Explore our website for articles, videos, and interactive content that dives even deeper into the topics we cover. You'll find a wealth of information to satisfy your curiosity. Support science education by sharing our content with educators and students. Our videos can be valuable resources for teaching and learning about the wonders of the universe. Thank you for being part of our journey. Together we can explore the mysteries of the cosmos, one fascinating discovery at a time. Stay curious, and we'll see you in the next video.